Hey, wonderful people. So I extend my warm welcome to you. Let's learn together. Join me as we learn about numbers, number system. So I will do it in three modules. Today I'll be talking about numbers one of three, and I'll keep it literally light. I'll keep it little light because as we go along the next two sections, I'll be hitting the depth. So I'll be going light. So we'll be seeing a prototype of what is coming in the next two lectures. So probably some of the concept that we do today is more a prototype of it. So the similar concept I'll be taking up into the depth. Of course, already there will be a variation, but we'll be hitting the real depth in the next two chapters, next two lectures on the numbers. So here we go with the first lecture on numbers. Before I take you into the numbers, let us try and understand what is the scope of this particular study with respect to various management entrance exams. So here we go. All right, this is the kind of a scope. So if you look at it, you might get as minimum as 2 questions, and you might get as many as 5 questions. Sometimes it would spell to even 6, 7 questions. Right? There is a direct implication or a direct application built on the basics that we learn in the next this lecture as well as in the next two lectures. Also nothing but when we are doing the algebra, surely already we are going to use some of the concepts that we learned today and also in some of the few other lectures. So we'll be using it in some of the algebra modules as well. So where especially the quadratic equations, surds. So we'll be using this. So especially the concepts of little bit of LCM, HCF would be using in algebra as well. We will try and explore that when we are doing the algebra module. For now, let's also keep in mind that just like the percentages was one of the very foundation lectures, this numbers one also forms a very foundation to the upcoming lectures and extended into the algebra as well. Not only that, already you will also find the applications of what we are doing today in modern maths or higher arithmetics, modern arithmetic, which we call it in permutations and combinations. So you'll also look into that. Not only that, so you will understand that the scope of numbers, of course, in the day-to-day life, in the day-to-day life, in counting, the measurements, various other things, right? So therefore, let's take this foundation lecture with let's understand this foundation lecture. So pay complete attention to this, because based on this particular lectures, there are 5 or 6 other lectures which depend upon a part of algebra, a part of modern maths. Not only that, the next two lectures of numbers depends on how well we understand today's lecture. Right, here we go. So let me say how I divided this particular lecture into various portions. Right, so if you look at this today, I'll be talking more about a divisibility. I will try and talk about divisibility. Primarily I will talk about divisibility, followed by I will make inroads into LCM and HCF, followed certain applications of LCM, HCF. I might not be hitting the depth of any of these particular topics today, because being the first foundation lecture, I will keep it really at the foundation level. So I'll be doing a part of I'll be talking about divisibility. Of course, the divisibility extends into remainder at some later stage, right? Therefore, so we'll be talking about the divisibility. So I'll talk about that, and maybe a part of LCM and HCF today, right, if time permits. Then in the next lecture, I'll be talking more about the factors and its applications, so which is also a function of a little bit of function of LCM, HCF, which I'll be using out there. Of course, I'll start next lecture with more on LCM, HCF and its application. Then I'll go into the factors and its applications. And the third lecture, I'll be talking about the remainders and its applications. That's how I classified my three lectures onto the numbers. Well, all right, let's get started on this note. So even before I get on to the divisibility rules, let me spend some time on classification. Let me spend some time on classification of numbers, which is very vital. On the face of it, when we say that the numbers, all right, so either we are talking about the real numbers, either we should be talking about a real number, or we should be talking about the imaginary number. On the face of it, when we talk about a number, either I must be talking about a real number, or I should be talking about an imaginary number, right? Say, hey, why we should talk about imaginary number? Sure, I'm not advising you to look into the complex numbers. So all I know, those who have done your 11th standard math, so you might kind of remember that, yes, you kind of talked about complex numbers, where you also came across the cube root of unity, 1 omega square, etc. Sure, I'm not dealing at that level, don't bother. Right, are we really talking about complex numbers when I mention the word imaginary here? Of course not. I'm not going into the depth of that. We are not talking about it. Rather, it is good to know it is imaginary from the management entrance perspective. Reason being, so when you are doing the quadratic equation, there sometimes you find the roots are imaginary. At that time, you should be able to understand that, oh, well, I got my roots as imaginary. What is imaginary number? When you do under root of a negative number, right? Under root of, say, -1. That's a classic iota people represented by I, root of -1. Not only root of -1, but even the root of -2 is imaginary, right? Root of -2 imaginary. 3 plus under root of -5 is also imaginary. Alright, you may say that a 3 minus 2 root of -7 is also imaginary. Likewise, you may say that a 3 is real, isn't it? Yes, 3 is real. Is this 2 real? Yes. But then I have an imaginary part here. Under root of -7 is an imaginary part here. All of them put together has become imaginary, because that's not no more real. Because there is a part of real, there is a part of real, there is a part of non-real, which is imaginary. Alright, now therefore all of them put together has become imaginary in total. Right? In totality, it has become imaginary number. It's good to know, because while you are writing your quadratic, you will come across this. So I will talk about it when we reach the quadratic. That's a discriminant. Already you understand a word. There's something called as a discriminant in quadratic equation. When we go there, sometimes the discriminant becomes a negative number, right? So that's when we get the roots are imaginary. From that perspective, I need to understand that, well, okay, I understood what is imaginary. Under root of something negative, under root of something negative, it is not sensible, becomes imaginary. Remember, but already now don't take it on the face value. Hey, is cube root of -8 imaginary? No, cube root of -8 need not become imaginary. Alright, no, because already you might say that, hey, this can be -2. Alright, just like a cube root of 8 is 2. Alright, the cube root of -8 can become 2. Alright, you need to take a judgmental call, proper judgmental call, which root you are taking. Based on that, you get your responses onto it, right? Yeah, okay. So I hope you got my point. Let me go further on to this. So therefore, imaginary numbers we understood. Now let's deal more of the real numbers, because our scope imaginary is just from that quadratic perspective. Otherwise, you don't find too much of scope on imaginary when you look at the management entrance exam perspective. So what matters to us more is the real number. All right, so let's take a look at the real number. On the face of it, you can classify the real number. So basically, you classified what? A number. Basically, here you classified a number. You said that a number can be either imaginary or the number can be real. That's what you said. So once we are under the real number, so we have two types. Either it should turn out to be an irrational number, or it can turn out to be a rational number. Right? Rational or irrational. Okay, rational number. So what is an irrational number? Already irrational number. Rather than a definition, try and recall how your teachers taught you with an example, because sometimes the illustrations, the examples, the stories are more powerful, right? So even when you go back to your childhood days, before they tell moral, what they tell, they will always tell the story first story. Because why? What gets absorbed is the story first, then they will come to the moral. Ultimately, they wanted to make that one point. So before making that one point, they told a story for 10-15 minutes, which was more important, which was more exciting. Same thing here. Already now, rather than definitions, you want to put them to the words. What is an irrational number? That may not be exciting, but the examples were exciting in the math. Alright, some of the examples given were always exciting. So what do you recall? Already irrational number. Sure, immediately what comes to your mind is root 2. Alright, root 2 is a classic example which comes to your mind, or it could be root 3. Alright, whichever way. These are the classic examples which first pop up in your mind without really understanding what is the definition. I'm sure alright, this is what you recall there. Root 2 and root 3. Alright, these are classic examples of an irrational number. Hey, can I say therefore? First, let's come back to the rational. So what is a rational number technically? A rational number is a 1, alright, which can be written in the form of p by q, where p and q are integers. Yeah, what about this p and q, where p and q are integers? Rational number is something which can be written as p and q, where p and q form integers. Alright, these two together should form the integers. Let me just quickly already illustrate what is integer before I come back to this. Let's take a detour. Let's go to the integers for a while. Let's go back to the integers for a while. Let me just illustrate what is this integer. Integers are of three types. Right? Integers can be classified into three types. What is that? Integers can be positive. Integers can be negative. They may be neutral. Integer can be neutral. What is integer? Neutral, 0. Because you never write plus or minus 0. Already you would have solved a lot of questions by now. Already right from your childhood days. You never write plus or minus 0. You might have written answers as plus or minus 1. You might have written answers as plus or minus 2. But you would have never written an answer called plus or minus 0. I'll give a simple example to illustrate this point. Probably you might have come across something like x square is equal to 4. What did you write? You didn't write x is equal to 2. If you are thinking x is equal to 2, you are wrong, right? Yeah, you are not completely wrong. You are not right as well. So what is right here? X is equal to plus or minus 2. You went on to write plus or minus 2, but you never wrote plus or minus 0, right? Yeah, correct. So let me continue. All right, therefore the neutral number, all right, neutral integer is 0. That's a neutral integer. So 1, all right, here on the number line, all right, here it is -1. You could have a 2 here, you could have a -2 here, there could be 3 here, -3 here. So this is what I meant by integers. I'm just clarifying it. I'm very sure that, okay, when I mentioned integer, things got into your mind, but then nevertheless, let me not take it for granted. This is what I mean by integers. Integers are of 3 types. Let me quickly dwell there. Let me dwell for some minutes there. So positive integers are also called as natural numbers. All right, now these are the words sometimes used in the exam, therefore it's important to know. Positive integers are also called as natural numbers, right? Yeah, and the neutral and the positive integers put together, this space, this entire space. Hey, what if I consider both the neutral and the positive positive integers put together? This together becomes a whole number. All right, this together becomes a whole number. Tell me quickly, what is the smallest whole number? Tell me quickly, therefore, what is the smallest number? That's right. All right, now that is 0. 0 is the smallest whole number. Okay, what is the smallest natural number? Quick, what is the smallest natural number? Very good. 1 is the smallest natural number. Super. Right, so therefore 1 is the smallest natural number, 0 is the smallest whole number. So whole numbers are also called as, sometimes to trick you, sometimes they also write the whole numbers as non-negative integers. Sometimes they also write the whole numbers as, they also call this as non-negative integers. They also call it as non-negative integers. Reason being, the moment all it people, some of the minds, right, some of the minds, the moment they say non-negative, positive comes into my mind. Absence of negative means they immediately think it is positive. So therefore all it, sometimes the 0 skips their mind, because author said that non-negative. Point is, integers are divided into 3 pieces. When I said that non-negative, I meant that this is not into consideration pool. When negative is not in the consideration pool, it's of course neutral as well as positive. Remaining 2 are in the consideration pool. Therefore another way of saying the whole numbers is non-negative integers. Be mindful about it. Sometimes they refer it as whole numbers, sometimes they refer it as non-negative integers, right? And then natural numbers are nothing but all positive integers. Now there is a classification of natural numbers, right? So natural numbers are further classified as natural numbers. If you look at the natural numbers, it can be further classified as prime numbers and composite numbers. All right, prime or composite. Natural numbers are further classified as prime or composite, right? We know that prime or composite, right? Which is that natural number. It is not that integers are classified as prime or composite. I'm sure all of you could recall that you never wrote a negative prime number saying that, okay, hey, -3 I wrote it as a prime number. Never ever in your life, right? You would have never done that in that. So therefore prime numbers, what they did, they looked at the natural number. Natural numbers are further classified as prime numbers and composite numbers. Therefore primes cannot be negative, composite cannot be negative. Positive natural numbers were classified in that fashion. Okay, so all of you might have recalled the prime number for that matter. What is the prime number? It should have minimum 2 factors. Let's write natural numbers, couple of them. Let's write couple of them just to illustrate this point. 4, 5, 6, 7. Let's say if I write like this. All right, now so let me all right, natural number. What is prime number? It should have exactly 2 factors, that is 1 and itself. That itself should be different from 1. You cannot duplicate that. 1 and itself. When you are saying and itself, you're talking about something else. It is not the same thing again. Hey, is it 1 and 1? No. It is not about 1 and 1. It is 1 and something else. That something else is called as itself. Therefore, all right, if you relate to the factors of 2, when you're writing the factors of 2, 1 is a factor and the 2 is a factor. Hey, what are the factors, by the way? I'm introducing that word probably already. If you have factors are the numbers which divide the given number, right? Factors are the number which divide the given number. In the sense, factors of 2 means 1 is a factor. Why? Because 1 divides 2. 2 is also a factor of that number. Why? Because 2 divides 2. 2 divides 2. Same way, let's say that 3. All right, when I look at the 3, all right, 1 divides 3. 2 does not divide 3, whereas 3 divides 3, right? So if you look at 4, all right, 1 divides 4, 2 divides 4, and 4 divides 4. All right, 4 divides 4. What is the prime number? Prime number should have exactly 2 factors. Therefore, this is prime. Therefore, this is prime. This is composite. Composite number should have more than two factors. More than 2 factors. More than 2 implies a minimum of 3. So look at 4. It has more than 2 factors. It has 3 factors in fact. Let's take a look at 5. Which are the numbers which divide 5? 1 divides 5 and 5 divides 5. What I meant by divide? Division is complete. Remainder is 0. 1 divides 5 and 5 divides 5. All right, what about 6? All right, how about 6? 1 divides, 2 divides, 3 divides, and 6 divides. Therefore, this is a composite number, prime number, prime number. Okay, you might have got this point now. I should have sufficiently taken the examples to help you out to recall. So what is prime number and composite number? Remember, 1 is an exception. 1 is an exception, right? Now, because 1 has only 1 factor. It is neither having 2 factors nor having more than 2 factors. Therefore, 1 is neither prime nor composite. 1 is neither prime nor composite. It's an exception, right? In all the natural numbers, every single natural number can be written as either prime or composite. It should turn out to be either prime or composite except 1. 1 is neither prime nor composite, because I've seen already now sometimes some of my students, so okay, if I take a quiz, sometimes they say that, hey, which is the smallest prime number? They say 1. No, smallest prime number is 2. Smallest prime number is 2. What is the smallest composite number? 4. See, look, when you're doing the quiz, you should be clear about little bit of boundary condition. Little bit of boundary conditions you should be clear. Hey, what is the smallest prime number? 2. What is the smallest, what is the largest two-digit prime number? 97. Probably now some of these things may be required there. Some of these things may be required there. Hey, what is the largest three-digit prime number? 997. Okay, what is the smallest three-digit prime number? 101. Right? What is the smallest two-digit prime number? 11. So these are the quiz. Now, so I want you to so you yourself develop that small kind of quiz where you kind of remember some of these numbers, which comes handy and useful. I already told you in one of my lectures, while I was taking before, so I said that remember all the prime numbers between 1 and 100, right? There are 25 prime numbers. I said remember all these 25 prime numbers. So I'm repeating it again. So because the prime has come in here, so therefore I'm repeating it again. It's good to know the 25 prime numbers which lie between 1 and 100, right? Out of all these numbers, 2 is the smallest prime number. You keep on writing it, and finally the largest number before 100 is 97, which is a prime. Largest prime number before 100 is 97. Great. Now, so this is something that you might have to kind of put it in perspective. Also another point I want to make here. So if you look at the prime numbers, and the point here, so all prime numbers except 2 and 3, all prime numbers except 2 and 3, these are the exception. Every single prime number other than 2 and 3 can be written as 6k plus 1, or 6 times of a multiple of a number minus 1, or 6 times of a multiple of a number plus 1. 6 times of a multiple number plus 1. Okay, hold on to this particular point. Wonderful applications will be built on this as we hit the depth. Now this is a very important point. There are a lot of tiny things to remember in numbers. They may not be massive in nature, but they're all very pretty tiny things. But the reflection of these tiny things is pretty important there, right? Yeah, 6k minus 1 or 6k plus 1. Every other prime number other than 2 and 3 can be expressed as either multiple of a 6 minus 1 or multiple of a 6 plus 1. All right, what do I mean? Let me say that 5 is an example of this. 5 is an example of this. Hey, why 5 is an example? You can write this as 6 into 1 minus 1. Hey, 7 is an example of this. Why 7 here? You can write this as 6 into 1 plus 1. Let's think of the next prime number, friends. 11. Okay, 11 can be written as 6 into 2 minus 1. Well, or it's just at the same time you can write 13, next prime number. I'm writing the sequence after 2, 3. What is the next prime number after 2 and 3? It's 5. I'm thinking, how can I write 5? So next I thought about 7. How can I write 7? Which column I can write? Okay, 11 is coming here, 13 is coming here, right? 13 is coming here. So you write this as 6 into 2 plus 1, right? What is the next prime number? 17. Very good. So 17 can be written as 6 into 3 minus 1, and likewise. But a word of caution here, the word of caution. So when you say that, hey, every prime number can be written as 6k plus 1 or 6k minus 1, I never meant the other way around. That is, hey, if you can write a number as 6k plus 1 or 6k minus 1, it becomes prime. No, it is one-way association. All right, one-way association. A prime number, so I meant this, a prime number. All right, now look at the arrow one side. If you know it is a prime number, then guaranteed. All right, now there is a stimulus, there is a consequence, right, as cause effect. If the cause, it's a prime number, given it's a prime number, then it can be written as either 6k, a multiple of 6 plus or minus 1. I never meant the other way around. Hey, what is other way around? I never meant that, hey, if you can write something 6k plus or minus 1, it becomes a prime number. No, I didn't mean that. All right, I didn't mean this part. All right, this arrow is not right. Okay, let me give an example to this. Let me give a quick example to this, what I meant by this. So take a simple example. Say, for example, all right, now, so you wrote 6 into 4 plus 1. Hey, what is 6 into 4 plus? You wrote 6k plus 1. You wrote it there, right? You wrote it as 6k plus 1, no doubt. Already you wrote it like that. Fine. So 6 into 4 plus 1 is 25. Already it's 25. Does this become prime? No, it does not. It does not. 25 is not prime. Okay, I hope everybody is clear on this, right? Now, therefore, the arrow leads on to one particular side. All right, arrow goes on to one particular side. Every prime number can be written as 6k plus or minus 1. But every number written in the form of 6k plus or minus 1 may not become a prime number. May or may not. Okay, yeah, there we go, friends. All right, now that's a little bit of a story, detour into the integers. What did I do? I was here, Well, technically, I was here at the integers. I took a detour to the integers. Then I briefed you on the integers. Okay, integers are of three types: negative, neutral, and positive. Then we understood that the natural numbers are also classified as primes and composites, etc. Let's come back. Let's come back to the lecture rational, because we were at the rational. Technically, we were at the rational number. Let us come back to that. Let us come back. Give me a second. Let me clear the board. All right, there we go. Right, there we go. Fine. So integers, we were there. Rational numbers. Every rational number should be written as P by Q, where P and Q are integers. Of course, as the common sense says, Q should not be 0. Right, Q cannot be 0, because we know that already if Q is 0, it becomes indeterminate. Right, you are trying to write 5 by 0. How does it make sense? It's an indeterminate. Tell something which is realistic in nature. All right, that becomes indeterminate there. Right, yeah. So therefore, all right, we know that condition. All right, we know that condition. So now look at that. Rational numbers, some people conveniently chose to write in two forms. Let me just highlight this rational number a little bit. Let me take this rational number. People conveniently chose it to write in two forms. They may say that, hey, I will write this rational number in the decimal form. All right, I may write this rational number in the decimal form. You may say, all right, rational number. Okay, I will write this rational number at times. Conveniently, I will write it in the decimal form. Sometimes I will write the same rational number in the fraction form. Well, I'll write it in the fraction form, because the decimal form and the fraction form exist. For both of them, both the decimal form as well as the rational form exist. So for example, okay, you wrote the fraction form as 3 by 2, let's say. The decimal form of this becomes 1.5. All right, 3 by 2, the decimal form becomes 1.5. Hey, what if I would have written it as 4 by 3? Fraction form 4 by 3. Is it a rational number? Of course, yes, because 4 is an integer, 3 is an integer. Of course, already it's a rational number. It's a rational number. Then what is the decimal form of this? Decimal form of this 1.3333 dot dot. All it, this never ends. This never ends. For let me quickly illustrate that. Let me quickly illustrate that. You don't believe this because there is no remainder, right? Yeah. So therefore, you will say that 3 1 time 3. So you got 1. You put a decimal place here. You get a 0 here. 3 times 9. Okay, you got 1. Again, you already put a 0. 3 times 9. The story goes on. This one story goes on. This 3 story goes on. Never ending. All right. Yeah. So therefore, what we call them? We call this as recurring decimal. Call it recurring decimal. Something appears again and again. Recurring means what? Something appearing again and again. There is a recurring decimal. Hey, what is this? This is terminating decimal. So therefore, in decimals, we have two names, right? And when I write the same fraction, fraction is fraction. Right, fraction is fraction there. All it is a fraction. When you write the fraction in the decimal form, it leads to two things. Either it leads to a terminating decimal, or it leads to a recurring decimal. Right, either it leads to a recurring decimal. All right. So let's get back to that. All right, terminating and recurring decimal. I will go back in a while. I'll come back to that. Now, even before that, let's come back to the irrational numbers. Let's come back to the irrational numbers for a while. Let's finish this thread. Otherwise, we'll take too many detours, will not reach the destination. We'll come back. All right, we'll come back. That's important point. There's a cat point there. Some of the exams, management entrance exams, put a question, beautiful question on that particular area, which I will illustrate in a while. So let's come back to the irrational numbers for a while. Irrational numbers, we wrote the classic example sometime back. We said that, hey, root 2 is irrational, root 3 is irrational. Even if you write 3 minus 2 root 5, that also becomes irrational. Why? Because hey, you may say that 3 is rational, you may say that 2 is rational, but root 5 becomes irrational. Therefore, put together, I cannot call it as rational. Put together, it becomes an irrational number, right? So therefore, that's becoming an irrational number. Okay, further, let's try and understand this irrational number. There are two special irrational numbers which I want to be mindful about. Hey, what are the which is that? All right, now, so one, pi is irrational. Oh, you may be wondering, some of you may be wondering, how on earth pi is irrational? Because pi is nothing but 22 by 7. Right, pi is nothing but 22 by 7. If it is 22 by 7, this is in the form of p by q, where p and q are integers. Already, if 22 by 7 is p by q and they are integers, how it becomes irrational? No, friends. Alright, now pi is not 22 by 7. Pi is very, very close to 22 by 7. Alright, pi is very, very close to 22 by 7. Alright, to make it convenient for mathematical purposes, converting the radians to degrees, or sometimes getting the areas of circles, or the circumference of the circles, just to make alright now to make the calculations little handy. They said that okay, the very closest value of pi is 22 by 7. In fact, it is not originally, it's actually not 22 by 7, because had it been 22 by 7, it becomes rational. No point calling it rational as an irrational number. Pi is very, very close to 22 by 7. Just remember, which means if you see the pi as a symbol, recognize that hey, it's an irrational number. Unless author gives a permission that hey, take pi as 22 by 7 and calculate, it should be treated as an irrational number. In fact, it is an irrational number, right? That's one. Second thing, now e is an irrational number. From management perspective, I need to have a special attention to these two numbers. Hey, where does this e comes there? One instance where you get this is log x to the base e, something like that. All it knows, you will be familiar. All right, if you have done a little bit of logarithms in the high school, you will write it as log x to the base e. Otherwise, while you are writing your exponential numbers, you also could have written this as e power x. You also would have written it as e power x, something like that. Right? These are the two popular instances where you would have come across e. What is this e here? Napier's constant. We call it as a Napier. All right, there's a mathematician by name Napier. All right, we call it as a Napier's constant. All right, Napier's number, Napier's constant. What is this approximate value of this? Again, from the mathematical perspective, e can be written as 2.718. From mathematical perspective, already you want to truncate it to 1 decimal place accuracy, 2 decimal place accuracy, or 3 decimal place accuracy. That depends on the kind of calculation that is expected. E can be taken as 2.718. Right? Yeah, and there are further applications of e. We'll come back to that. There are further applications of e in little bit in a sense in algebra. There we'll come back to that. We'll come back there. But look, have a special attention that pi and e are irrational numbers. These two are important for us from the management entrance exam perspective. Further, let's go back. Let's understand that we were here. Let me come back here, recurring. Let me come back here, recurring. Recurring here. So can irrational numbers can also appear in the decimal form? That's a question. Can irrational numbers also, can they come in the decimal form? Why not? They also can come in the decimal form, because here I wrote a lot of examples. None of them were in the decimal form. None of them were in the decimal form. Is it possible that just like the rational numbers appear in the decimal form, you said that the rational numbers do appear in the decimal form? That's right. So similarly, can the irrational numbers can appear in the decimal form? Why not? Even they can appear in the decimal form. They can appear in the decimal form. Let me give an example here. Now look, I'm writing a number. I'm writing a number here. My number is 1.23 double 23 triple 23. All right, triple 23. Then I will write 4 2's followed by a 3 dot dot dot. Hey, what do you mean by dot dot? It's never ending, because I give a pattern to you. First I wrote 2 followed by a 3, double 2 followed by a 3, triple 2 followed by a 3, 4 2's followed by a 3. Or even a child will tell that next what I'm going to write. Child will tell 5 2's followed by a 3. After that 6 2's followed by a 3. Is there a pattern to it? Of course there is a pattern to it, and it's a never ending pattern. It's never ending a pattern. Therefore all right, it is what? It is non-terminating. Basically you are trying to say that man, this is non-terminating. You can't call it as recurring. Let's be very careful in using the words. All right, this is non-terminating. It is not recurring. This we call it as a non-terminating. Because why it is not recurring? Recurring means something should appear again and again and again. So something is not appearing again and again and again. Let me write that example for you. N. If I write this n as 1.23, 23, 23, 23 dot dot dot. Now the child says that hey, 23 23 23. Now here the point is, what is recurring again and again and again? 23 is appearing again, 23 appearing again, 23 appear again, which means I can copy 23 and keep pasting it. This is called as recurring. Therefore this is an irrational number, whereas this becomes a rational number. Right, now this is called as a recurring decimal. This becomes a recurring decimal. Right, the one on the top cannot be called as a recurring decimal. Irrational number, hey, can I call it as a recurring decimal here? Can I call this as a recurring decimal? No. Instead I should be calling this as a non-terminating decimal, because there is a pattern to it. It's a non-terminating, but I cannot call it as a recurring. Okay, so now therefore both rational numbers as well as irrational numbers, they do appear in the decimal form as well. Great. Well, because sometimes when you are taking some of the management entrance exams, some trivial questions can be based on this. So yeah, they did appear. I'm not saying that okay, there were no questions. There were, why I'm calling them, simple questions can appear, which we can close it in 30 seconds time, provided I have a clear understanding about the classification, because it just takes about 30 seconds to close such questions, right? Good. So here we go, friends. I briefed you about rational number, I briefed you about irrational number. Let me continue with my classification before I come back to one more point there. All right, so far we are clear about rational, we are clear about irrational. So let me go a little further. So I'm here, rational and irrational are clear. Right, my rational and irrational are clear. So rational numbers are further classified as fractions and integers, right? They can be further classified as fractions or integers. All right, it should either turn out to be a fraction or it should turn out to be an integer. Integer I covered. All right, I already had a pre-detour and I finished this. Integers is covered. All right, I said that integers are of three types. All that is done. All right, now more or less integers is covered. So what about the fractions? All right, now again the fractions, you may say that a proper fraction or an improper fraction, right? There is a proper fraction versus improper fraction. What is a proper fraction? Proper fraction is one in which the numerator, fractions are what? There is a numerator and a denominator, right? P by Q format, where P we call it as a numerator, the Q all it is nothing but the denominator. We already understood Q cannot be 0. You write Q 0, then nothing makes sense there, right? Yeah. So therefore, what is a proper fraction? Proper fraction is a 1. All right, proper fraction is a 1 in which all right, the numerator is greater than, numerator is less than the denominator. Numerator is less than denominator. Example 2 by 3. Example 2 by 3 is 2 by 3 becomes one of the examples of a proper fraction. Hey, what about an improper fraction? Improper fraction is one in which numerator is greater than the denominator. Numerator is greater than denominator. One of the examples, reverse 3 by 2. One of the examples 3 by 2. Now this also called it improper fraction can also be written as mixed fractions. Improper fractions can be expressed as the mixed fraction. What is the mixed fraction? This can also be written as 1 by 2. This can also be written as 1 by 2. Okay, now don't worry too much about the improper fractions to mixed fraction. That's not a study here, fine. So we need to just understand that proper fraction. Point here is, hey, why proper fractions are important? Yes, all right, I'm introducing the words which are important. I am not talking about anything, all right, just from the intellectual perspective. So it has to also lead to the result. It should be profitable. Whatever we discuss has to be profitable from the entrance exam perspective. Otherwise, just from, oh, it intellectually it is very stimulating, does not make sense. Does not make sense, right? Now it should be profitable as well. Hey, why I'm talking about this proper fraction? Because you hear this either in the exam, you hear this, or the professors will come back, lectures will come back, or they will faculty come back and they will use this word, where in the geometric progression of infinite terms. All right, when you want to write the geometric progression up to infinite terms, the common ratio has to be a proper fraction. If the common ratio is not a proper fraction, then geometric progression up to infinite terms is not possible. Therefore, whatever I am expressing here, each and every term has an attention. Already you need to pay attention to every term because all of that is important. Right now, I will generally don't speak about things which are not profitable. Does not make sense. We need to be profitable with the time that we talk about. Great. All right, let's go further, friends. Let's go further. All right, that's about this. Now, it's a point here. Let me come back to a CAT question. One of the important management entrance exam question, be it a CAT question or be it a SNAP question. So, how to convert recurring decimal into a fraction? Because sometimes the people face a difficulty here. Hey, don't they face on terminating decimal? They don't. Don't they face it on a terminating decimal? They don't. Say for example, 1.5 is a terminating decimal. I said, okay, convert this to a fraction. No problem. Nobody has a problem converting terminating decimal into a fraction. Why? All right, now what is this 1.5? 1.5 divided by 1. That's what they write. Okay, multiply both numerator and denominator by 10. They write this as 15 by 10. All right, so therefore they'll simplify. They'll say that 1.5 is nothing but 3 by 2. Let me take another example. Hey, what if I write my number as 1.23? If I write like this, no problem. Well, the 1.23 is nothing but 1.23 by 1. What should I do? Multiply both sides by multiply both numerator and denominator by 100. If I multiply, it becomes 123 divided by 100. This cannot be simplified. So what? This itself is the answer. This itself is the answer. Right? In the earlier case, 3 by 2 could have been the answer. So therefore, there is no problem. But the point is, if I write this number, take a look at this particular number, 1.3333, it goes on, right? What the point here is 1.33, now dot. This is going on and on and on. Well, it is going on and on and on. Now the problem comes. Here comes the problem. Should I multiply by 10? Should I multiply by 100? Should I multiply by 1000? Because you're not seeing an end to this. You are not seeing an end to this. So if you multiply by 10, you'll be writing it as 13.33. by 10. That's how you will be writing this. Okay, if I multiply both side, both numerator and denominator, because what is in the denominator, it's 1. If I multiply by 100, you will write it as 133.333 dot 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 divided by 100. It is still not a fraction, so you are not getting it. Therefore, how do I express? That's a beautiful cat question. Right, now let's go here. So classification is clear, friends. I basically talked about the classification so far. Right, and about the integers, remember, prime 2 is the smallest prime number, 2 is the only even prime, all other primes are odd in nature. Also, all prime numbers other than 2 and 3 can be written as, or at 5 can be written as 6n plus or minus 1, or 6k plus or minus 1. It can always be expressed like that. That's what we talked about the integers. All right, when we came, then we talked about the rational and irrational numbers. In irrational numbers, two special numbers, pi and d, are special. I said that already. You better remember pi and d as the special irrational numbers. And then we talked about rational and irrational number do exist in the decimal form as much as they exist in the other forms. All right, they also exist in the decimal form. Good. Then we talked about, all right, then now we are talking about how to convert a recurring decimal into fraction. Let's take a look at this. Let's take a look at this. Then I'll detour. Then I will come back to a few other questions. Let's take a look at this. Let's complete this. Then I will brief further on. So now look at that. All right, you have a n here, 1.333. Now remember, guys, all right, listen to me carefully. Very carefully listen to me. All right, carefully you listen to me. On this particular number, right, on this number, so you realize that how many digits, all right, how many digits after the decimal place? The decimal place is the barrier. Look at the decimal place. Look to the right of the decimal place. Check how many digits are appearing again and again. You will see that only one digit is appearing again and again, which is 3. Which is 3. 3 just appears again and again. Copy that 3 and keep pasting it. Copy that 3 and keep pasting it. Okay, again the barrier, come here. Let's first look at the decimal place. After the decimal place, which side I need to be looking? Look on to your right. Look to the right of the decimal place. All right, how many digits are appearing again and again? You say that 23. Not one digit, 23. You have to keep already, you have to take the 23, keep pasting it again and again and again. Good. All right, let's take a look at the third example. The similar way, let's take a look at the third example. Great. All right, now look after the decimal place. Look after the decimal place. How many digits are appearing again and again? Which are those particular digits? Which are those particular digits? Look to only to the right of the decimal place. What comes to the left of the decimal place does not matter. Is there a pattern? Is there no pattern? Does not matter. What matters is what is coming onto the right hand side of the decimal place. Only that does matter. Okay, good, great. All right, let's take a look here. So what is repeating again and again? It is 4, 5. Very good. 3 is not repeating. 3 is there as a filler in between. 3 is there. But what you can copy? You can copy 45 and then keep pasting it and then keep pasting it. 4, 5, 4, 5, 4, 5. You can keep pasting it. There is a pattern to that, right? Yeah, good. All right, there we go. All right, therefore, let's take a look at this. All right, therefore, how do we convert it? Now, listen to me. If one digit is repeating, I put a circle here. There is only one digit which is occurring after the decimal place, which means you copied 3 and then you went on to paste it again and again and again. Because you copied only one digit, multiply both sides by 10 power 1. This is the entire equation. Multiply both sides of the equation by 10 power 1. If you multiply both the sides, your equation will not change. It won't become an inequality. It remains an equation. Very good. Okay. So what should I be doing it here? All right, what I should be doing it here? Hey, how many digits are repeating again and again? 2 digits. That is 23. Because 2 digits are repeating, multiply both sides by 10 power 2. What if there were 3 digits repeating after the decimal place? Then multiply both sides by 10 power 3. Then multiply both sides by 10 power 3. Okay, that's algorithm. Okay, I multiply and do what? Let's come to that point. Let's come to that point. Hang on. Let's come to that point. So, okay, so what you are trying to say is, okay, if one digit is repeating after the decimal place, multiply both sides by 10 power 1. If 2 digits are repeating, multiply both sides by 10 power 2. What if I have 3 digits are repeating, multiply both sides by 10 power 3. That's an algorithm. Okay, I multiply and do what? Let's take a look of that. Let's take a look at that. Okay, so what we are saying, n is equal to 1 point. This was the given number, 3, 3, 3, 3, etc. dot dot dot. Good. We already decided this factor. One digit is repeating. So far we are clear. All right, we already had a closure at that. We are clear that, okay, so one digit is repeating. Great. That is my n. Multiply both sides. What we already said that we have to multiply by 10. Let's multiply. Therefore, you are saying that 10n is equal to, because you multiplied both sides by 10, 10n is equal to 13.13.333, etc. dot dot dot. 13 point. Why? Because you multiplied that by 3, multiplied that by 10. When you multiply by the 10, what happens? This decimal place gets shifted here. That's it. It just gets shifted, pushed by that. Therefore, instead of 1.33, it would become 13.33. All right, that would simply become 13.33. Good. So what I do now? Solve. What do you do now at this stage? You solve. Solve is what? Subtract the first equation from the second. Call this as the first equation. If you want, you call this as the second equation. I'm advising you that, okay, to solve it 2 minus 1. Do 2 minus 1. Okay, if you do 2 minus 1, what do you get? 9n. 9n is equal to 12. And then what happens to all these threes? They get cancelled. This 3 gets cancelled with this gets cancelled like this. All the threes after the decimal place will get cancelled. So all you are left with is 13 minus 1, which is 12. All right, which is 12. Therefore n is nothing but 12 divided by 9. All right, if you simplify, this would become 4 divided by 3. Simple one. All right, pretty simple one. Simple algorithm. What I wanted you to know on this particular algorithm: decide after the decimal place how many digits are repeating, multiply by those many powers of 10. If one digit is repeating, multiply by 10 power 1. Here two digits are repeating, therefore multiply by 10 power 2. Let's do this. There would be a clarity. Let's do one more. You automatically get a clarity. Okay, let's write it here. N is equal to, what is given to me? N is equal to 1.23 and so on. All right, 2 3 and so on. Good. So I need to multiply this by what? 100. Very good. So if I multiply by 100, it becomes 100n. All right, it would become 100n. So therefore you're writing it as 100n is equal to, when you multiply this by 100, the decimal place shifts here. All right, it shifts here. Therefore you kind of write this as 123.232323. That's how you are writing this. All right, that's how you are writing this. Okay, now do what? Solve. Solve means what? Subtract the first equation from the second one. This is 1 full n, right? 1n means what? 1 full n. Therefore 100n minus n essentially becomes what? 99n. And similarly 123 minus 1, here 123 minus 1, which becomes what? 122. Hey, what about others? Rest of them gets cancelled. All these terms get cancelled. So therefore you are saying that n is nothing but, all right, 122 divided by 99. 122 divided by 99. Okay, it's a simple algorithm. I hope all of you would have got this by now. Okay, now listen to the next one. Pretty interesting question. All right, this third question is a very interesting question. Let's understand. Can I multiply this by 100 now? Because we said that two digits are repeating, 4 and 5. We already circled it and kept it ready. 4 and 5 are repeating. Can I multiply this by 10 power 2? Can I multiply this by 10 power 2? Let us see what happens if I multiply like that. So n is equal to, you wrote this as 2.345. You're writing this as 2.345, sorry, 34545, etc. This is what you're writing here. Fantastic, that's fine. So you multiplied by 100. If you multiply by 100, the decimal place shifts here. Decimal place shifts here. You are trying to say that n is equal to, all right, 100n is equal to, you multiplied by 10 power 2, because that's what you said here. Multiply by 10 power 2. It would now become 234 point, because the decimal place has shifted here. All right, 234.54555 54. All right, 5. All right, now so you are writing from here 54. That's what you are writing here. 54. You are writing 54. You are writing 54. You are writing 54. You are writing 54. That is the shape it is taking now. All right, that is the shape it is taking now. So it is now looking little cumbersome. Hey, it's not very convenient to solve all the numbers here. All right, solve all the numbers. So what you do in this case is you just do a slight modification. Look, so here what happened? All two threes got cancelled perfectly. So all threes here after the decimal place got cancelled, but you are not able to cancel like this. You are not able to cancel like this because there is a problem. There is some problem here. All right, I'm not able to cancel like that. I'm not able to cancel like that. So what you will do on this particular case, all right, the best way to handle. So either you solve there and then go one more step, or here what you do is, all right, now one other way to deal with this is, shift the decimal place here. Go back to this, guys. All right, go back to this problem. What you do is, hey, why can't I shift this decimal place to this place first? Let me shift and then apply the algorithm. All right, and then apply the algorithm. I hope you're all with me here. It's a very critical point. Do it with me very carefully. Shift the decimal place. What do you meant? First multiply both sides by 10. 10n. N is given to me, friends. N is given to me. What you do is first find 10n. 10n is equal to 23.454545. 10n is equal to 23.454545. We can write it like this. Very good. All right, now so now is the recurring started right after the decimal place? Has the recurring started right after the decimal place? Yes. See, look, if you go back to every other problem, let me go back to every other problem. Recurring started right after the decimal place. Recurring started right after the decimal place. Only in this problem, the recurring did not start right after the decimal place. Now, what did you do? You brought it to the form where recurring started right after the decimal place. How did you do that? Just suitably multiply by 10 or whatever you do it. Now, the recurring started right after the decimal place. Now, how many digits are recurring, which means how many digits are repeating again and again? 2 digits. Therefore, what you should do? Multiply by 10 power 2. Now, multiply by 10 power 2. Okay, if I multiply by 10 power 2 this entire equation, 10 is already there. You are multiplying by 100. It becomes how much? 1000. It becomes how much? 1000. Therefore, 1000 yen is nothing but 2345 dot 454545. All right, that's what you get there. Now I can simplify this. All 4 5s get cancelled. So all of them gets cancelled. So therefore I have my response here. I have my response here. What is the response? 990 n. 990 n is also nothing but all it knows. So 990 n is also nothing but all it you have 2 3. All it 2 3 2 2. All it 2 3 2 2. In other words, n can also be written as 2322 divided by 990. I hope all it with these three examples you kind of learned. Of course, both are even numbers. Can I simplify by 2? Yes, you can simplify by 2. Well, that's not a worry. But I wanted you to understand that okay, how to convert the recurring decimal into fraction. All right, how to convert the recurring decimal into fraction. Absorb this first. If you are doing this for the first time, absorb this first. I will come back to the similar slide maybe in some other lecture. Then I will tell you just by looking at this how you can write this. Because first I want you to absorb this. Let's not hurry up. Idea is not to hurry up. Idea is to first absorb the material, absorb it, how it has to be dealt, how algebra is working behind, how the math is working behind this. Then we will come back and put it in the sweeter portion. How do I quickly write this numbers, all right, without really getting into the hassle of writing all of this. I'll come back to this maybe in the next lecture or towards the end of this lecture today, all right, whichever way it is feasible. I'll come back to this by the time you absorb. All right, once you absorb, let's come back. All right, maybe in the next lecture we'll come back and we'll quickly write it to the perspective. Okay, there we go. All right, now that's one portion of the lecture. Let's continue with our study. Let's continue with our study. Recurring decimal portion is done. Let's now understand what are co-prime numbers. All right, what are co-prime numbers? Right, co-prime numbers that are mutually prime. All right, now we say it to be mutually prime. It is not that prime numbers become co-prime, friends. All right, it is not about if the number has to be a prime to become a co-prime. No. All right, numbers need not be prime for them to become co-prime. They need not be prime. All right, but then all right, just like co-brothers. Assume that a family has two sisters. All right, there are two siblings. All right, both are sisters. Right, so in a family, parents, husband, wife, and then they have two kids, both daughters. Now both these daughters married. All right, now two gentlemen. Now they become co-brothers. Hey, should they be brothers before? Of course not. They need not be brothers, but they become co-brothers. Alright, you would have heard about this co-brothers and co-sisters. How the co-brothers need not be brothers. How the co-sisters need not be sisters. Alright, no, need not be necessarily the sisters. They need not share the blood necessarily. Right now, similarly, co-primes need not be prime. Simple way of applying the language. Alright, language works similar. Whether you talk about numbers or you talk about relationships, language is language. Right? Yeah, let's go here. So what do I mean by this co-prime? Let me think about this. Now look at this classic example I give. Classic example you remember from schools. The story, the classic example your teacher would have said, is 4 a prime? Is 4 a prime? Answer is no. 4 is not a prime. Is 9 a prime? Answer is no. 9 is not a prime. Are they co-primes? Answer is yes. Co means what? Minimum 2 should be there. All right, with the 2 should be there. Co-brothers, co-sisters means what? 2 people should be there. You cannot look one number and say that this is the co-brother. What do you mean? You are looking at one person and calling him as a co-brother. You are looking at one woman and calling it as a co-sister. Does not make sense. Co means a pair. All right, now there must be at least 2 here. So 4 and 9 are said to be co-primes because they don't share any common factor other than 1. 1 is the only number which divides both of them. 1 because 1 anyway divides every single number. 1 divides everything on earth. Right? The 1 is the only number which divides. Therefore, what you are trying to say, all right, what is co-prime? Simply put, co-primes are nothing but they cannot share any common factor between them other than 1. Right? Yeah. What are the factors of 4? All right, 1 is a factor, 2 is a factor, 4 is a factor. Fantastic. What are the factors of 9? 1 is a factor, 3 is a factor, and 9 is a factor. Hey, which is the common between them? 1 is the only common factor between them. Therefore, 4 and 9 are said to be co-primes, although they need not be primes. In fact, all right, both of them are not primes. None are primes here. None of them are primes here, but they are said to be co-primes. This is a classic example you remember from your schools, friends. All right, classic example. You always remember certain things through stories, through examples. Examples is a powerful way of learning. Right, parallel examples are a powerful way of learning, or stories is the powerful way of learning the morals. Similarly, examples are the powerful way of learning, or it be it the words, or be it math, whatever be that. Right, so this is all right. Therefore, all right, now 4 and 9. This is the kind of classic example you remember. Okay, little more to that. Let's go there. Already, you also might have remembered this. All right, two consecutive numbers are always co-primes. Two consecutive natural numbers are always co-primes. Two consecutive natural numbers are always co-primes. Right? Yeah. What is that? For example, if I say that 2, 3, are they co-primes? Yes. Okay. Let us randomly write something. Hey, I wrote 90 or I wrote 95, 96. Neither 95 is prime, 96 is prime. But then 95 and 96 taken together, you take them as a pair. They become co-primes. That's what I mean by two consecutive numbers. They are always co-prime to each other. All right. Now that's very important point. Two consecutive numbers are co-prime to each other. Similarly, two consecutive odd numbers, they also become prime numbers. Two consecutive odd. A simple example, 3, 5. All right, simple example, 3, 5. All right, two consecutive odd numbers. Okay, let me take another example. What about 93, 95? Yes, they are also co-primes. All right, 93, 95. Neither 93 is prime nor 95 is prime, but taken together, they become co-primes. All right, there is nothing which is other than 1 which divides them parallelly. 1 is the only number which divides 93 and 95. There is no other number which divides both of them simultaneously. Right, simultaneously. All right, therefore we say these two numbers are said to be co-primes. These two are co-primes to each other. Right? Yeah. So therefore any two odd numbers. Now don't quickly extend it. Sometimes this happens in my class. Right now, because I said two natural numbers, two odd natural numbers, some people quickly jump and say that, oh, okay, next is two consecutive even numbers. No, friends, two consecutive even numbers does not work. For example, 2, 4. Two consecutive even numbers. They're always divisible by 2. In fact, all right, now 2. All right, now 2 is the number which divides two consecutive even numbers for sure. All right, 2 is the number. 2 becomes the number there. All right, now 2 always divides them. Any number, yes. All right, even if you take 94, 96. Even if you take 94, 96, or let other than 1, in addition to 1, of course 1 divides. In addition to 1, 2 also divides. That's my point. In addition to 1, here also 1 divides 1 and 2, or 2 and 4 for sure. 1 divides. In addition to 1, 2 also divides. Hey, are these the only two common numbers? Yes. All right, these are the only two common numbers. Right? Therefore they are not co-primes. Why they are not co-primes? Because it is not only divisible by 1, it is also divisible by 2. It is also divisible by 2. Therefore they are said to be co-primes. Therefore, all right, they are not said to be co-primes, because in addition to 1, it is also divisible by 2, and hence two consecutive even numbers are not co-primes. Odd numbers, yes. Natural numbers, yes. Consecutive natural numbers, yes. Consecutive odd numbers, yes. Don't quickly extend all and say that even also, yes. No, even or not, yes. All right, even or not, yes. You know the reason here, right? Yeah. So therefore, already any two prime numbers, they will be always co-prime to each other. Any two prime numbers for that matter. Okay, 2 is one prime number, 97 is another prime number. Will they be co-primes? Yes. All right, will they be co-primes? Yes. Okay, yeah. In other words, if you just understand the HCF and LCM clearly, which I come to the fag end of the lecture, if time permits, I will come there at the fag end of the lecture. Otherwise, I will take it in the next lecture, as I said. Okay, so HCF of HCF of co-prime numbers is 1. HCF is 1. Even if you don't understand, don't bother at this stage. We'll come back to that at a later stage. HCF of co-prime numbers is 1. All right, highest common factor. HCF is highest common factor. That's a little bit of story about the co-prime numbers, which are very, very important. Co-prime numbers, as much as prime numbers are introduced, co-prime numbers are also very important. Co-primes come in pairs. Let's understand that, okay, that has to be dealt in pairs. All right, yeah. So there's a little bit another part, odd and even. There are some simple questions which appeared in CAT just based on the odd or even, the nature of the number. Is the nature is odd or is the nature is even? We are all very clear of the definition. Even numbers are divisible by 2. We are pretty clear about them. Everybody would be clear about it. Even numbers are divisible by 2. Odd numbers, of course, not divisible by 2. Of course, not divisible by 2. In the sense, they always leave a remainder of 1. Or leave a remainder of 1, because when the number is divided by 2, there are only two possible remainders. Either 0 should be a remainder or 1 should be a remainder. If 0 is the remainder, number becomes even. If the 1 becomes the remainder, the number becomes odd. The number becomes odd or even, right? Odd or even. Okay, couple of things. Now this is what I'm more interested in, because the CAT asks questions based on the simple property of addition properties or multiplication properties. What is true for addition? Let's try and understand here. Hey, now 3 baskets. Let me put it like this. I have two numbers, number 1 and number 2. number 1 and number 2. If the first number is even and the second number is even, I add them because addition, right? Addition, right? N1 and N2, there is a resultant number. Therefore, what is the result here? Already, what is the result? Result means I don't want to know the number. I want to know the nature of that number. Has it become odd or has it become even, right? That's all I want to know. Even plus even. Assume that the first is even, the second is even, the result is even. Result is even. Okay, what if I take the first number odd and the second number odd? I take the first number odd and the second number odd, the result is still even. You can take any numbers for your in your mind, friends. You can take any number, any even number in your mind. Hey, let my n1 be 2 in the first case, let my n2 also be 2 or 4, whatever you want to take. Now what is the resulting number? When you added them, it has become 6. The result has become 6, right? Therefore even plus even is even. Similarly, odd plus odd, already you can take for second example as 1 and 3. Now look at the result here. The result has become 4, which becomes even. Odd plus odd is even. You can take any numbers in your mind as I'm talking, right? What about all it now? What about I take one odd and one even? The first one is even and the second one is odd. If I take odd and even, the result becomes odd. Result becomes odd. Simple like all it now. So what if I take 2 plus 1? The result has become 3. Does the order matter? You know that in the addition, order does not matter. What do you mean by order does not matter? Can I take the first number as odd and the second number as even? The result is same because both are same. Both are same. Already order does not matter in addition. But what is the order? Therefore the order does not matter there. So that's about the addition story. It's important. We'll come back to that. I'll take a simple illustration on this. As you start solving from different modules, well, you'll come across this parity there. Even if not directly, there is an indirect form where you come across this in probabilities and some other calculations. You do come across them. You do come across them. We will come back to that at a later stage as you go through this journey or journey of your aptitude preparation for these management entrance exams. We will come across them. All right, we will come across them. Let's take a look at this multiplication here. Let's take a look at the multiplication. Okay, another point before I do that. Whatever we discussed for addition is true for subtraction. Is true for subtraction. What if I had a minus sign between them? Your results remain same. It's a difference. Or a difference is also fine. Difference is what? Bigger number minus smaller number you do. Or a bigger number minus smaller number. Take n1 as a bigger number. Take n2 as a bigger number. It's easier. Otherwise you'll get the negative answer. That's fine. That's also fine. Odd even, all it odd and even. That's also fine. So what I'm trying to say, whatever you understood for plus, sum of two even numbers is even. The difference of two even numbers is also even. Say for example, I have two numbers n1 and n2. I took the difference between them. Take the first even number as 10. Take the second even number as 4. What is the difference? Therefore, what is the result? Result is also even because difference of two even numbers. You are writing difference of two even numbers also becomes even. All right. Now, whatever is true for addition is also true for subtraction. Sum or difference of two even numbers is even. Sum or difference of two odd numbers is also even. Likewise. All right. Likewise. Okay. Let's go to the next one. Multiplication properties. Important. Let's go to the next part, multiplication properties, right? Yeah, so I have two numbers n1 and n2. I have two numbers n1 and n2. So already what is the result look like? Hey, what if I multiply an odd number with an odd number? I multiply an odd number with an odd number. The result is odd. Alright, product of two odd numbers is odd. Okay. Hey, what if I multiply two even numbers? The result is even. The result is even. Hey, what if I take one even number and one odd number? Any order, the result becomes even. The result becomes even. You can take some simple numbers in your mind. You can take some simple numbers in your mind. When I'm saying odd and odd, you can take 1 into 3. Already for the first one, when I'm saying odd into odd, you can take 1 into 3. 1 into 3. When I'm saying even into even, you can take 2 into 4. Or you can take 2 into 4. Right? When I'm talking about even and odd, you can take it as 2 into 1. You can take 2 into 1. All it simple numbers. All it whenever I'm saying, not only in this class, in any other class in general, when I'm making these remarks, all right, you can quickly flash some numbers in your mind and you can verify these facts. In fact, all these are primary school issues, right? Primary school issues. Let me make a couple of comments here. All right, now here, let me make one comment here. Product of any number of odd numbers is odd. Product of any number of odd numbers is odd. Hey, not only two numbers. Hey, what if I have taken some three numbers here? Odd. Hey, what if I have taken four numbers here? Odd. So for example, a 3 raised to power 100 is odd. 3 raised to power 100 is odd. I don't know what is this number. Neither you. All right, not you also know. You can't claim that I know. Come on, tell me. All right, no, neither you know. I know. I don't know. You don't know. All I know is it's an odd number. 3 raised to power 100 is an odd number because product of any number of odd numbers is odd. Not only two odd numbers. You can take three odd numbers. All right, now what did I do here? 3 I wrote 100 times. Basically, you are trying to say the 3 into 3 into 3 into like this. Doesn't matter how many times you take. As long as they remain odd, your result remains odd. Your result remains odd. Right now, that's a property of indices. I'm talking here. That's what I'm talking here, the property of indices. So what I'm trying to say is, look, all right, if you take an even number, you raise to any power, your result remains even. You raise it to any power, result remains even. Which means I took 2. 2 raised to any power, will it be even? Yes, except 0. Except 0. Now don't write that, okay, I will write 0 and prove you wrong. No, I didn't mean that, right? Or don't write 0. All right, some exceptions are there, just like the language also has some exceptions. Math also has certain exceptions. We need to apply it mindfully, certain properties, right? Therefore, you don't write n is equal to 0, write any natural number. N is a natural number. Take it as a natural number. 2 raised to power any natural number, the result has to be even. Similarly, odd number raised to any natural number, the result has to be even. Result has to be odd. Odd number raised to any natural power, the result has to be odd. All right, in the sense, okay, if I say, all right, 3 raised to power n, will the result be odd? Of course, yes. Always the result is going to be odd. I guess, all right, it's making sense to all of you. I hope I didn't rush through this. It made sense to you, right? Addition rule, addition and the subtraction. Then we talked about the multiplication. Then already extension of multiplication is, of course, the indices. Expression is indices. What if I put an indices to that? How does this entire dynamics work? Right? Good. That's a little bit about the properties here. Let's look at some of the applications now. Let's look at some of the applications built on this. Okay, here is a question for you, friends. Here is a question for you. Quickly apply this. In a minute's time, let me know the answer to this. In a minute's time, let me know the answer to this. Very good. Great. All right. Yeah, answer is none. None, right? There is no such answer there. All right. Why? Because 6 times of x is an even number. 6 times of x is an even number. Why? 6 into anything is an even number. Find the number of integer solutions to this equation. That's what author said. 6 times of anything integer. All right, now author said that x and y are integer. You can't take a fraction and prove that it becomes odd. All right, because if you write 6 times of half, it becomes 3, it becomes odd. Author clearly said take integer and prove me, all right, how many ways. Find the number of integer solutions. All right, x and y has to be integer. So if x and y are integers, then 6 times of x is always even. Similarly, 4 times of y is always even. What even plus even would become? Even plus even would become another even number. Well, together it would become even number. But what is the outcome here? Outcome is an odd number. Therefore, you will say that 0. Answer to this question is 0. There is 0 solutions to this particular equation. All right, 6x plus 4y is equal to 75. It is never possible to get the outcome as 75 if you take x and y as integers. As long as you take x and y as integers, you will never get an odd outcome, right? Pretty simple example. Pretty simple example. Let's take another one out here. Let's take another one out here. Take another one out here. Take a minute. Take a minute. Another one. Great, you did it. Nice. Okay, it says that x, y, z are distinct integers. They are distinct. X and y are odd and positive. See, one way of dealing with this is what? Take odd numbers. They're distinct, author said. So therefore, one way of dealing with this, take it as 1 and take it as 3. That's one way of dealing with this. One way of dealing is that z is an even and positive. Take it as 2. Technically, you're saying that 1, 3, 2 are my numbers. Which of the following option is correct? All right, now that's what author is trying to say here. All right, that's what author is trying to say. You can say that x minus z, you can write this as minus 1 square. Let x minus z as minus 1 square, because x is 1 and z is 2. You can write it as minus 1 square times of how much? Y. What is the value of y there? 3. Therefore, what is 3 times of 1? Which becomes 3. But author says that it's even here. Therefore, A is ruled out. Let A is ruled out. Let's go to B. Here, what is y square there? Y square is 3 square. Let y square is nothing but 3 square. Okay, what is x minus z? X minus z is minus 1. So therefore you are trying to say that, okay, what is this particular value here? You are trying to say that minus 9. Minus 9 is odd. Minus 9 is odd. Therefore B is ruled out. B is ruled out. Similarly, C is also ruled out. Only one thing, all it which would work it out in your favor is Z. Only one thing that would work it out in your favor is Z. Okay, sometimes there will be much deeper questions built on this particular concept, where you can't really take 1 2 3 kind of, because there will be about 25 26. All right, now 26, they'll use all alphabets A B C D E F up to Z, stand for some of the odd numbers or some of the even numbers, and they create a question here. Yeah, how do you analyze during that particular point in time? The analysis is simple. All right, now, so you will look at this. If one of them is odd, one of them is even. So odd minus even, the result becomes what? The result becomes odd. Odd square into y. What is y here? Y is another odd number. Y is another odd number. Therefore, all odd numbers, the result becomes odd. The result becomes odd. That's how I wanted you to interpret here. Hey, what is this y square here? Odd square. What is this y square here? Odd square. Hey, what is this x here? X is an odd number. Hey, what is z here? Even number. Hey, what is the difference? Odd and even. It becomes another odd number. Therefore, what is the overall result here? The overall result is also nothing but another odd number. The overall result is therefore nothing but another odd number. Odd into odd, we said that product of any number of odd numbers becomes a odd number. Therefore, we are kind of aware of this. Well, this is the systematically, this is the way I wanted you to solve this. Well, this is the way I wanted you to solve this, so that when we hit the depth, I don't have to keep assuming the numbers 1 2 3 4. Rather, I'll be working by using the concepts. Right, we'll be working by using the concepts. Great. Let's go to a few other concepts here. Divisibility. Alright, that concludes the classification. I took about an hour to illustrate you a bit of things about the classification. So what are the things to be kept in mind in classification, which is pretty important, worth the time spending there. Now let me take you on to the divisibility. Probably the next 1 hour I'll spend on divisibility. If I conclude little early, if you're able to grasp it and conclude little early, then I will also make inroads into LCM, HCF. If not, all it will conclude with the divisibility in the next 1 hour's time. Pretty important topic, because the understanding of divisibility also results, this also has the effect on your remainders, which is another important topic, right? Therefore this becomes very essential for us. Understanding of this becomes very, very essential for us, crucial. So let's try and understand this. Divisibility by 2. So we all know that already. If you take simply an example, say you have you have a number. Let me take an example of a number. Say my number is 1 2 3 4 5 6 7 8. I wrote a 8-digit number. This is a number. Right? This is my number here. So I wrote this number as 1 2 3 4 5 6 7 8. 8-digit number. I have a 8-digit number. So question is, is this number divisible by 2? Yes. Where do you make a decision? Divisibility rule for 2 is just look at this digit and make a decision. Is this divisible by 2 or not? Look at only the last digit. Last digit, nothing but the units digit. Look at the units digit of the number and make the decision. You look at 8 and you say that because 8 is divisible by 2, therefore the entire number is divisible by 2. I don't have to worry about the remaining 7 digits. Rather, I just have to worry about the last digit. That's a divisibility rule for 2. Pretty good. Divisibility rule for 4. All right, that's also simple. Last 2 digits. Now this time you say that, hey, I look at the last 2 digits. Divisibility rule for 4. Last 2 digits. You look at 78 and you say that, man, this is not divisible by 4. 78 is not divisible. 76 is divisible. After that, 80 is divisible. Therefore 78 is not divisible, and then you say that, okay, it is not divisible by 4. But remember this one more thing. All right, now this small thing skips the mind of the people. Teachers would have said them during the high school or the primary school. Now in the high school, because in the primary school they will not introduce too much of remainder there. So divisibility rule also tells you the remainder, why it is not divisible. In case it is not divisible, reason is the remainder. All right, it also tells you the remainder. I don't have to divide the entire 8-digit number. All right, to check the divisibility rule for 4, I just took 78. I divide by 4 here. All right, I'll take this 78 and I would divide this 78 by 4. Alright, I would divide this 78 by 4, right? Therefore, you will say that, okay, so the alert 4 1 times 4, therefore you have 38, 4 9 times 36. All right, 4 9 times 36, therefore 2 is the remainder. Look, this 2 remainder is also a remainder when you divide this entire number. In fact, when you divide this entire number by 4, this is precisely the remainder that you get, right? Therefore, remember, every divisibility rule also tells you the remainder, or it gives the remainder. In case it is not divisible, it tells you the remainder. Knowing the remainder, you can do some adjustments. The idea is what? Knowing the remainder, you can do certain adjustments. So therefore, I can add another 2 so that it becomes divisible. For that, what? I should know what is the remainder there. So I should know what is the remainder there. Good. Let's go to the next one. What's the divisibility rule for 8? Last 3 digits. Last 3 digits. All right. What's the divisibility rule for 8? Last 3 digits. Last 3 digits, which means I should have taken 6 7 8. I would have checked it whether it is divisible by 8 or not. So pattern here, remember, all it pattern here, all prime raised to power n have a pattern, especially 2's have a pattern. Listen carefully. All it 2 power 1, all it, that is nothing but 2. Divisibility rule for 4 is 2 power 2. Divisibility rule for 8 is 2 power 3. Divisibility rule for 16 is 2 power 4. Divisibility rule for 35 is 2 power 5. Divisibility rule for 35 is nothing but 2 power 5. So when I say divisibility rule for 2, divisibility rule for 2, just look at this last digit. All right, that power 1 is saying that this is how you can remember. Look at the last digit. Good. Okay, this is 4. What is 2 power 2? 4. When I say divisibility rule for 4, look at the last 2 digits. Look at the power. Look at the power and make a decision. Look at the last 2 digits. Okay, when I say 2 power 2 power 3, then nothing but 8. Divisibility rule for 8. Look at the last 3 digits. Look at the last 3 digits. 8. Divisibility rule for 16. Look at the last 4 digits. Divisibility rule for 32. Look at the last 5 digits. Okay, if you are specially preparing for CAT like an exam, till 32 is important. Alright, till 32 is an important. In the sense, knowing that, okay, last 5 digits are important, it should be known. Last 5 digits. Divisibility rule for 32 does come in. 16 and 8, etc. are very, very commonplace. They're very, very commonplace. Right? Therefore, that is something that you got to keep in mind. Now, this is precisely the divisibility rule for 5s as well. For 5s as well. I want to understand that is this number divisible by 5? You have to look at the last digit. Is this number divisible by 5 square? Last 2 digits. Is this number divisible by 125? Last 3 digits. Why 125? 5 cube. Is this number divisible by 625? 5 power 4. From CAT perspective, till here it is important. Last 4 digits of the number to be divisible by 625 is important. I'm just saying that, okay, from CAT perspective, divisibility rule can be extended. There is no problem extending the divisibility rule. But the point is, okay, from test perspective, till where I should know, till 625 I've seen the questions. Right now I have come across the questions till about 625. That's what divisibility rule for 5, divisibility rule for 25, divisibility rule for 125, and the divisibility rule for 625. Till here I need to be careful, which means I don't have to panic when somebody says that, hey, there is a huge number. Let me know when this number is this number divisible by 625 or not. Simple. Consider last 4 digits. Take couple of seconds, or it take about a half a minute or a minute. Close it. 625 is a nice number. Close it using that particular number. Tell that whether it is divisible or not, or tell that this is the remainder out here. For example, let's say that, hey, is this number divisible by 125? No, it is not divisible by 125. Last 3 digits you have to look at. Fine. So, but what is the remainder then? Therefore, what is the remainder when this 8-digit number is divisible by 125? I don't have to divide the entire number by 125. I just have to consider the last 3 digits and divide by 125. I will consider this 675. I'll consider this 675. I'll divide this by 125. Consider this, 678. I'll consider this 678. And then I will divide by 125. How many times? 125. 5 times 625. 125 5 times, already it becomes 625. Good. Alright, therefore what is the remainder here? 53. So now you are saying that, look man, already this particular entire 8-digit number, in this entire 8-digit number, when divided by 125, the result is going to be 53. Remainder is 53. It is not completely divisible. Knowing 53, what you can say? You can say that reduce it by 53, it becomes divisible, or increase it by a suitable value, it may become divisible. Alright, those decision can be taken. Okay, so this is the story of powers of 2s and powers of 5s, right? This is the story of powers of 2s and powers of 5s. Great. Now let me come to the next point here. Okay, all of you are clear about the 2s and 5s. Still here I covered. Alright, not only just 2, 4, 8 and 5, the entire story of powers of 2s and powers of 5s are covered. Let's go to the next part here, friends. Let's take the same example. Let me clear the board. I guess already everybody is learning something here. Yeah? I guess everybody is learning something. Good. I'm keeping it a little lighter. I'll be hitting the depth in the next class, but I am keeping it lighter because these fundamentals are very, very important. These concepts are undercurrent to so many other concepts that we are going to learn in the future, even into the extension of quadratic equations and permutations, combinations, etc. All right, let's take a look here. All right, let's go to the 3 here. I'm here with respect to 3. So we had this number 1, 2, 3, 4, 5, 6. Let's say that, okay, if I'm writing this particular number, all right, 5, 6, 7, 8, whatever. All right, we wrote till 8 here, right? Yeah, this is the number. Okay, here, so divisibility rule for 3. All right, divisibility rule for 3. What is that? From the school, you should have learned that it is the sum of the digits, in the sense, okay, I have to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. All right, if the sum of the digits is divisible by 3, then the entire number will be divisible by 3. The sum of the digits should be divisible by 3, then the entire number will be divisible by 3. Great. So you would have added these numbers. Okay, summation of n natural numbers will come handy if the number is very long, friends. Therefore, all it is good to understand certain summations. Let me tell you in this class itself. So all if I say that, hey, sum of n natural numbers, I wanted to add like this. All now up to n dot 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 up to n until 8 is here. What if I wanted to add this up to n? Fine. All right, now in that case you would have written that sum of n natural numbers, we write it as summation n, which is nothing but n into n plus 1 by 2. All right, n into n plus 1 by 2. What if there were squares on this? What if there were squares on this, in the sense, okay, what if I had 1 square plus 2 square plus 3 square up to n square? Sum of is solid, sum of the first squares of first n natural numbers. Then you would have written this as n into n plus 1. Alright, you would have written this as n into n plus 1, 2n plus 1 divided by 6. Alright, this is what you write there, right? This is what you write there. Alright, similarly, what if it is a cubes of the numbers 1 cube and 2 cube, 3 cube, and so on? Some of the cubes of the first n natural numbers. They would have written this as n into n plus 1 by 2, whatever you wrote earlier, by 2 whole square. N into n plus 1 by 2 you wrote before also. Alright, you wrote before also. This time all you do is what? Square this function. Square this particular number, which becomes the sum of the cubes of the first n natural numbers, right? Now in addition to that, hey, what is the sum of the sum of first n odd natural numbers? What is the sum of first n odd natural numbers? Say for example, alright, you need to understand my statement. Sum of first 3 odd natural numbers, which means I'm saying that first 3 odd natural numbers means 1, 3, 5. First 3 natural numbers. If it is the first 3 odd natural numbers, the score is number is n square. What is n square here? How many numbers you wrote here? 3 numbers. Therefore, you should be writing it as what? 3 square. Alright, that's the sum. 5 plus 3 plus 1, which becomes 9. Alright, sum of the first n odd natural numbers. Similarly, what is the sum of the first n even natural numbers? Sum of the first n even natural numbers. What is that I'm trying to say this time? 2 plus 4 plus 6. So this is 3. First n even natural numbers can be written as n into n plus 1. So in this case, you would have written as 3 into 4. 3 into 3 plus 1, which is nothing but 4. If you add these numbers, you get the result as 4. 2 plus 4 plus 6. Yeah, these are some of the things that you should be knowing. Some of the things you should be knowing, because I got an opportunity that here. Therefore, I just made you illustrated that particular point. 1, 2, 3, 4, 5, 6, 7, 8. This is what you have. Therefore, all right, now I just illustrated this point. Hey man, these are must-know factors. These are must-know factors. All right, if I take a detour and illustrate something there, please remember it is a must-know. Otherwise, I will not make a detour. No point making a detour. Sometimes I make a detour from the concept. The concept was I was talking about the divisibility rule for 3 and 9, but I made a detour. The reason I made a detour is it reminded me of something you must know. You must know, right? Yeah, okay, fine. Fair enough. Let's go on. Detours are important. So whenever I take a pit stop, the detour, please remember that they're very, very important there. Otherwise, I will not make a detour. I will focus on the journey, right? If you are doing a detour, there is something very important. Fine, let's continue here. Let's continue our study. Divisibility rule for 3. What did we say? Sum of the numbers, sum of the digits of the number. I would have done this quickly. Knowing this, already would have said that, okay man, this is 8 into 9 divided by 2. 8 into 9 divided by 2, 36, which means you added them. Adding like that also is fine, because 1, 2, 3, 4, 5, 6, 7, 8 does not take much time. Hey, what if it's a big number? Then it would have taken a little more time. Then some patterns may come, or maybe in this kind of question or in any other kind of question, the summation comes handy. That's my point there. Fine, let's go here. 36, this is 36. Point is 36 divisible by 3? Answer yes. Therefore, this entire 8-digit number is divisible by 3. Hey, what if about 9 here? For 9 also it is like this, but don't extend now. Just like you did for 2 and 5, a word of caution: quickly don't extend this. Say what I meant this. Listen carefully, I meant this. What I meant is this. So you have, alright, now this is prime raised to power n. Alright, it also follows that series. 3 power 1. What did you say? Sum of the digits of the number. Very good. 9. Alright, 9 also same. Sum of the digits of the number. 3 square. Alright, that's also say 3 square is 9. Divisibility rule for 3. Sum of the digits of the number. Divisibility rule for 9. Sum of the digits of the number. Now don't say that, okay, fine, alright, now so I've attended a lecture. They talked about 2 power 1, 2 power 2, 2 power 3, 5 power 1, 5 power 2, 5 power 3. Oh, there is another one, 3 power 1, 3 power 2. Hey, don't rock like that. Hang on, right? Hang on. All right, it's 27. So now don't say that for 27 also sum of the digits of the number. No, it is not sum of the digits of the number. I'll come to this in my third lecture, part 3. I will come there. All right, what is the divisible rule for 27? I will come there. I will come there. I'm doing a very basic part here. 3 and 9 is sum of the digits. For 3 and 9, it is sum of the digits, not for 27. Not for 27, 81, etc. Right? Yeah, sum of the digits. Solid. This is sum of the digits. Hey, is 27 important from the exam perspective? Yes, 27 is important. Right? 27 is important. I will come to that. I will come to that particular pattern later. I will come to that. Good. Okay, that's about 3 and 9. That's about 3 and 9. These are the issues that you learn in the primary school. All these are the issues 2, 4, 8, 5, 3, 9. All these are the issues of the primary school. I'm making it clear that the issues of primary school are very important and they are clear in our mind. They are clear in our mind before I proceed. Okay, let's go to the next one. 11. Let's go to this 11. 11, you know that, okay, this is nothing but the difference between the sum of the alternate digits of the number. Very confusing statement. Let me write an example. Let me write an example. I said, what did I say here? All right, now this is nothing but the difference between the sum of the alternate digits of the number should be divisible by 11. Should be divisible by 11. Look very confusing here. Very confusing here. Let me write an example. Let me write an example to illustrate this. Right, because sometimes the sentences look pretty confusing. Right, they look like complex and compound statements. Right, just like complex sentences, difficult to understand. Some definitions are so. I agree. Or so. Okay, let me take a simple illustration here, friends. Let me take a simple illustration here. Say my illustration is 8, 4, 7, 2, 1. Let's say this is my illustration. So what is that I'm trying to say here? I'm trying to say that, okay, add the digits from the units place. Add the digits from the units place. Units place. Sum of the digits, alternate digits starting from the units place. Start from the units place. Already units place is 1. Alternate. Jump. 1 plus 7 plus 8. 16. Already you called it as 16. Alright. Then sum of the alternate digits starting from the tens place. Alternate digits starting from the tens place. What is it? 6. Alright, what is it here? 6. Alright. Therefore, take the difference between them. That is units place minus tens place. It's never t minus u. It is always u minus t. Okay. Therefore, what did you get here? 10. That is the remainder. This is the remainder because you got 10. Hey, what if you would have got 11 here? What if you would have got 11 here? Fantastic. If you would have got 11, then this entire number is divisible by 11. Alright, now because you got 10, is this 10 divisible by 11? Answer is no. Then what is that? This is the remainder itself, which means when you take this 5-digit number here and you divide this by 11, you get 10 as the remainder. 10 as the remainder. So if I just change this particular digit to 2, for example, if I change it to 2, then this 16 becomes 17, then this 10 would have become 11, then 11 divides this 11, then you would have said that, man, this entire number is divisible by 11. I hope all of you got this. All of you got this. Remember, it is always units place and tens place. Units place minus tens place. It is never about tens place minus units place. In that case, you will not get the remainder. You will just get to know whether it is divisible by 11 or not, but you will not get to know the remainder. Okay, let me illustrate that example. Let me take that example to you. Okay, why it is like that? Let me take that example. Let me make it clear to you. Here itself, let me make it clear. Let me make it clear. Say, for example, I took this number as 1, 2, 1, 2, 3. Let me take 1, 8, 3, 4, 2. Right, something like this. I took another 5-digit number here, friends. I took another 5-digit number here. Yeah, what is the sum starting from the units place? What is the sum starting from the units place? 3 plus 2, 5 plus 1, 6. Yeah, what is the sum starting from the tens place? What is the sum starting from tens place? 8 plus 4, 12. Yeah, what is the units place minus tens place? Units place minus tens place has become minus 6. Question remains same. Is minus 6 divisible by 11? No, minus 6 is not divisible by 11. But therefore, this number is not divisible by 11. Very good. If this number is not divisible by 11, then what is the remainder? Remainder is minus 6. Man, how remainder can be minus 6? Something left over is minus 6. How on earth it is possible? Correct, it is not possible. I and you, both of you know this. Something that is left over cannot be minus 6. What do you mean by minus 6 chocolates are left? No, what is left? You tell me. After you ate, what is left? Say 0. There cannot be minus 6 chocolates left. That's a remainder here. Remainder cannot be less than 0. But you got minus 6 here. Great. So minus 6, then what is the positive remainder? You know from your high school that you should add the divisor. If minus 6 is the remainder, add the divisor. What was the divisor here? You are checking divisible rule for what? Alright, that you cannot forget, right? You are checking the divisible rule for 11. If you are checking the divisible rule for 11, add the divisor. Minus 6 plus 11, the result has become 5, which is the remainder. Alright, otherwise minus 6 also is the remainder. but you can't give the final answer as negative. If you can't give the final answer as negative, then add back the divisor. So this can be done. All right, this can be done provided all right, you are doing it in the order. You always take u minus t. I hope my point is very clear to you. Right, my point is clear to you. It should be crystal clear. It should be clear to you with this example. Great, let's go to the applications now. All right, that's a little bit about the divisibility. Okay, let me talk a little more. Let me talk a little more before we go to the applications. Let me talk a little more here. All right, there's another pattern which comes here. Another pattern which comes here. Okay, now if you look at all these numbers that we have done, they were prime by nature. Hey, what do you mean by prime by nature? I will tell you. All the divisibility rules that you have done so far were of the form p raised to power n. They were all of the form p raised to power n. What do you mean? You took 2 as the prime number. First prime number is 2. Already you took 2. You discussed the divisibility rule for 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. I said that for cat this much is important. Great. Okay, then we talked the next prime number which is 3. Alright, p raised to power n. You talked about 3 power 1, 3 power 2, alright, 3 power 3. Till here for cat is important, but we stopped here. I said that I will come back to this later. But the point is there were one single prime number, 3 power 1, 3 power 2, 3 power 3, etc. Good. Then we talked about 5 also. Then we talked about 5. We talked about 5 power 1, 5 power 2, 5 power 3, 5 power 4. Alright, we said that for cat up to 5 power 4 is important. Okay. Then we talked about the next prime number. What's the next prime number? 7 power 1. Oh, we didn't do this 7. You may say that, hey, I didn't do this 7. Correct. Alright, this I will do it in the third class. I will do this. 7 is important for cat. Alright, 7 is an important number. We'll come back to that. 7 is an important number. Great. Let's go further. Let's go further. After 7, what? 11. 11 power 1 we did. All right, 11 power 1 we did. So therefore, whenever you did, all right, now 13 is also important for cat. 13 is the next prime number. That's important. Whatever I circled, I'll come back to them. Right? 3 power 3, I will come back to them. 7 power 1, I'll come back to them. 13 power 1, I'll come back to them. From the management entrance exam perspective, these are the other 3 numbers you should know from whatever you did. But not only this, there is something else. Hey, what if all right, the given number, all right, what if my divisor, here is it's a divisor, right? Divisibility rule. Your divisor was of the form p raised to power n. Hey, what if your divisor is of the form p raised to power n, p1 raised to power n, and p2 raised to power m? Some divisors are like this. Some divisors are like this. Yeah, what is that I'm trying to say? I'm trying to say that resolve, all right, now resolve your divisor into primes. Let resolve it into primes sometimes. Yeah, what do you mean by resolve it into primes? I'll come to this. 6, think about it. 6 can be written as what? 2 power 1 into 3 power 1. What do you mean? For 6, you don't have a direct divisibility rule. This divisible by 6 means it should be divisible by 2 as well as 3. The number should be divisible by 2 as well as 3. Resolve them into primes. What is that resolving into primes? Write them as primes. 2 and 3 were primes. Write it. Resolve it into primes. Therefore, divisibility rule for 2, for everybody on earth, the number has to be divisible by 2 and the number has to be divisible. There are rules, friends. We cannot change the rules of the game. We cannot change the rules of the game. The rules are rules. Okay. Now think about it. What is the divisible rule for 12 therefore? What's the divisible rule for 12 therefore? For everybody, the rules remain same. It is same. Resolve it into primes because it is not made up of one prime. It is made up of multiple primes. How do you write this 12? It is 2 power 2 into 3 power 1. What do you mean 2 power 2? It should be divisible by 4 and it should be divisible by 3. The number should be divisible by 4 and it should be divisible by 3. It should be divisible by both of them. Say for example, let me take an example here. Let's say that okay, my number is 1, 2, 3, 4, 5, 6. Alright, 1, 2, 3, 4, 5, 6. Hey, is this number, alright, is this particular number divisible by 12? I'm asking, is this number divisible by 12? What is that we are saying here? This number should be divisible by 4 and it should be divisible by 3 here. It should be divisible by 4 and 3. Let's check. Is this number divisible by 4? Last 2 digits. Answer yes. 56 is divisible. Okay, the divisibility rule for 3. What is the sum of the digits? 21. Is sum of the digits is 1, 2, 3, 4, 5, 6, 5, 6. The sum is 21. Hey, the sum is 21. Is 21 divisible by 3? Yes, because it is divisible by 4 as well as 3. This number is divisible by 12 as well. This is divisible by 12 as well. Hey, what if it was divisible by 4 but not by 3? Then it is not divisible by 12. Alright, then it is not divisible by 5. What if it is divisible by 3 but not by 12? Still it wouldn't have been divisible by 12, right? Yeah, simple one. Alright, that's how you will understand this. Alright, that's what you are trying to say. So divisibility rules are fixed. These are 2 patterns. Alright, this is the first pattern. Either it should belong to this pattern or the rule should belong to this pattern. Now think about it, guys. What is the divisibility rule for 18 therefore? What is the divisibility rule for 18 therefore? Divisibility rule for 18 is 2 power 1 into 3 power 2. 3 power 2, do you know? Yes, we know. Divisibility rule for 9, we know some of the digits. Do I know divisibility rule for 2? Yes, it's the last digit. Therefore, if I give you a 7 or 8 digit number, you will not panic because you know how to find it. Divisibility rule for 18. Now think one harder one. You think, guys, you think 72. You tell me divisibility rule for 72. You tell me what is the divisibility rule for 72. Tell me, 30 seconds. Tell me what is divisible rule for 72. Very good. Very good. Right, 72. How did you write it? Already you decomposed it. You realized that this can be written as 2 power 3 into 3 power 2. See, what is that you are trying to do? You did this, isn't it? Alright, what all you did is this, something like this. You took this 72. Alright, you took this 72. Then you started dividing. First you thought about a prime number. Which prime divides it? Okay, 2 divides it. 2 how many times? 36 times. Then you again thought about it. Which prime divides it? Again 2 divides it 18 times. So then which prime divides it? 2 divides it how many times? 9 times. Which prime divides it? 3 divides it how many times? 3 times. Is 3 already a prime? Yes. Therefore stop. So when you stopped it, what did you do here? Alright, you write 2, 2, 2. What is this? 2 cube. That's what you wrote it here. 2 cube. Yeah, what is this? 3 into 3 here? 3 square. That's what you wrote it here, right? Yeah, all of you would have understood. Smart enough to understand this. That's what I'm doing here. That's what I'm doing here. Therefore, these are the derived ones. These are derived ones. You can derive also because you know the basic ones. I'll call this as the basic ones. Alright, because you know the basic ones, you can do the derived ones. These are the derived ones. Basic ones versus derived ones. We can derive many. We can derive many based on the exam or whatever the numbers that they're asking. We can derive quite a handful of things. Alright, now quite a few handful of things. No worries on that. Alright, yeah, good. So let's go here. Therefore, let's go to the examples. Alright, that summarizes the divisibility rules. Let's now do the examples for the next 20-30 minutes. Alright, another 30 minutes, friends. We're about to finish the lecture in about 30 minutes. Let's do the examples now. Alright, let's do the examples. Let's learn. Alright, let's learn about divisibility. So how do I apply this? Knowing these concepts, how do I apply? Take a look. Alright, now he has given a 5-digit number. Alright, 2,700. Alright, 67,809 M. Alright, where M is a digit. Alright, it's not mentioned here. Take M as a digit. Alright, what is the value of M? Technically, it's a 5-digit number which is divisible by 8. What is the value of M? What is the divisible rule for 8? Last 3 digits. What's the divisible rule for 8? Last 3 digits. So let me go in detail for you. First question. You are saying that 8, 9, M. Alright. This number should be divisible by what? 8. Fantastic. 8 one time. 8. Great. Alright. Therefore, alright, now 8 one time. 8. Therefore, alright, now so here 8 one time. 8. It is 0. So what happens next? 9 comes. Alright. 8 one time. 8. All right, therefore 1 and M. So 1 and M is a digit. Now author said that, man, it is divisible by M. He is not asking that is it divisible. He is saying that it is divisible. Great. All right, let me write the tables of 8. All right, 8 one time is 8. 8 two times is 16. All right, 8 three times is 24 and so on. Hey man, there is 1 and M here. All right, there is 1 and M. 1 followed by M, 2-digit number. There is only one 2-digit number which starts with 1 and then followed by something. Therefore, you will say that, okay, this is 8 two times here. Therefore, this has to be 16. Alright, thereby it becomes divisible by 8. You can't write M value as anything else. Therefore, M value has to be 6. Therefore, M value has to be 6. What is the value of M? Therefore, 6. You are saying that, man, the value of M is 6. Pretty simple one. But I want you to do it a little faster, not like this. It looks like a child's play here. Looks like a child's play here. Sure. Alright, when we do the first example, let us keep it like that. Let's keep it like that. But thereafter, we need to pick it up. We need to pick it up. Alright, we cannot be babies, infants. Alright, we need to grow. Fine, fair enough. Let's go here. Well, there is a number which is divisible by 9. What is the value of M? Divisibility rule for 9. What is that? Sum of the digits of the number. Keep adding for now. So therefore you have a 3 added to 5, alright, which is 8. 8 plus 8, 16. 16 plus 9, 25. 25 plus 2, 27. So far you are saying that, man, these digits are 27. Alright, so addition of these particular digits has become 27, right? Now that is 3 plus 5, 8 plus 8, 16 plus 9, 25 plus 2, 27. It has become 27. Now you are saying that, hey, 27 plus M should be divisible by 9. Alright, now M can be 0. Therefore, M can be 0. Alright, look at the word I'm using. Can be 0. M can be 0 or M can be 9. Or M can be 9 because 27 plus 0 is divisible. Hey, what if I make it 27 plus 9? Still divisible. Don't write 27 plus 1 and say that it is divisible by 9. No, 27 plus 9 is 36. That's fine. That is divisible. Therefore, M can take two values. Alright, therefore, it is can be 0 or 9. Alright, what is the value of M? There will be choices. Alright, one of the choice can be 0. Alright, one of the choice can be 9. There could be another choice, alright, which is 8 or something. There could be another choice which says more than one of the above. More than one of the above, or suitably 1 and 2, or whatever, both 1 and 2 or more than one of the above. They will suitably construct the options. Based on that we will pick it. Alright, based on that we will pick it. Great. Alright, let's go to the next one. Let's go to the next one. I hope you are all getting the applications. Yeah, you must be enjoying it. right? I hope you are enjoying the lecture. Great. Let's carry on here. Find the greatest value of m. Now look at this. All it know, which means there may be multiple values of m, just like we did earlier. Find multiple values of a here, because therefore he is asking greatest value of a, such that this particular number becomes divisible by 9. All right, this number becomes divisible by 9. Greatest value. All right, which means a can take multiple values. Otherwise, where is the question of greatest and least? All right, the words, the way they use the words, greatest means there are multiple possibilities. Otherwise, why do you use the word greatest if there is only one single value there? Fine, let's take a look here. Add the digits, divisibility rule for 9. Let me add this. 8 plus 6, 14, 14 plus 7, 21, 21 plus 4, 25. So far, what is that I'm seeing sitting with? 25 plus a plus b. I'm sitting with this. I'm sitting with this. This entire thing should be divisible by 9. Because up to 25 I'm fine, which means 6, 8, 7, 4, that's comfortable. All right, there, till there it's comfortable. But then I have two variables, that is a and b, where a and b are the digits. All right, where a and b are the digits. So therefore you are saying that 25 plus a and b should be equal to 9. Look at that. What are the values a can take? 0 to 9. Yeah, what are the values b can take? 0 to 9. All right, 0 to 9. So because author said that greatest, all right, greatest expectation management. When you said greatest, I know that theoretically the best value of a is 9. Theoretically the best value of value is 9. Validation is what I want to do. Validation is what I want to do. So you always do some expectation management as you learn along. Sure, I will talk about this expectation management as we start getting into the deeper aspects of this aptitude learning through our journey, right now. So because this is not the only end of this, we just commenced our journey. As we go through this particular journey, I will talk about this, because once you start getting hang of these concepts, you will start doing the expectation management. You don't approach these questions with a blank mind. You approach with an expectation, right? Similarly, when you're sitting in this class, you have some expectation. You are not approaching with a blank mind, right? You are not approaching without any expectation. There is certain expectation, right? Just similar here, there is some expectation management which I can do even before I look at the choices or something. Greatest value of a is what? 9, because the range is 0 to 9. So if 9 is it possible, because choice is there, I will put that and check. That's an easier way. Let us say 9 here. Great. 25 plus 9, 32. All right, 32. Then what is the value of b here? 2. All right, therefore the value of b is what? 2. All right, that way it becomes 36. All right, that way it becomes 36. 36 is divisible by 9. I had some expectation management. I know that the greatest value a can take theoretically is 9. I just made a validation check. I checked, validated it. All right, I did validated it. By validation, I found that 9 works. 9 works. Therefore, the best answer is going to be 9. The greatest value is going to be 9. Hey, why did you say? What is the least value? Had he asked the least value, what would I have done? Same equation. I would have written 0. 25 plus 0. Had he asked the same question, man, tell me what is the least value of this? What is the least value that he can take? I know from my expectation that the range is 0 to 9. I would have plugged 0 here. I would have plugged a 0 here. All right, once I plug a 0 here, what else I could have plugged here? Plug 2. This becomes divisible by 9. Therefore, the value of b becomes 2. All right, so that it becomes 27 and divisible by 9. Therefore, the boundary conditions, best is 9 and the worst is 0. The least is 0. Had it been least, already would have said that it is 0. What is the best? Best is 9. So how could I easily solve this particular question? Doing certain expectation management on the desert. All it might have helped you to close it faster and better. But you need to learn that skill of expectation management. It is a little important. All right, that's important there. Fine, let's go here. Let's go here. Let's go to the next question. Let's take a look at this question. Okay, I'll give a minute. Think about it, friends. Think about it. I'll give a minute for you. A minute time. Think about this question. Yeah, tried it. Great. Let's try it together. All right, let's do this together. Let's try this. Nice, nice. You might have got some answers. See, very important here. Alright, if this is divisible by 8 as well as 9, what is that author is trying to say? Look, this is divisible by both 8 and 9. Just like we learned in the second aspect, right? Derived ones, it should be divisible by 8 as well as 9. The word look here, can be. Pay attention to grammar, friends. Pay attention to grammar. Well, this is an exam question, right? This is an exam question. I'm taking it. So pay attention to the grammar. What is he saying? Can be means what? Possibly. Possibly means what? There should be many answers. Otherwise, why you are talking possibilities? Alright, you talk possibilities when there is more than one set of an answer that is possible. Alright, that's where therefore you are possible. Therefore, there is no hard and fast rule that one value works. Alright, one value works. You can of course answer it by using the answer choices, no doubt about it, right? No doubt about it. But let's also be mindful about the question. That's my point. Can be. Hey, can I plug the answer options and check? Why not? You can do that, right? Yeah. So first, let me crack this 8 portion. Let me crack this 8 portion. Why? For 8 portion, I don't have to look at the full number. I don't have to look at the full number. I just have to look at I just have to look at the last 3 digits. That's advantageous, because for 9 I have to look at the full number. I don't have to look at the full number. I can just look at the last 3 digits and make a decision. Great. Let me take that 9, 6 and B. 9, 6 and B should be divisible by 8. Should be divisible by 8, right? Yeah, let me do that. 8 one time, then you have 2 8 2 times 16. All right, then you have a B. All right, you are just left with B. B is a digit, friends. B is a digit. It's already divisible. What is the value that B can take here? All right, because so far you are 0. So 0 followed by B. 0 followed by B. B can be another 0. All right, this B can be another 0, because what if I write 960? My point is 960 by 8 divisible, friends. 960 by 8 is divisible. What is the other number? 8. What is the other number? 8. Can I write this as 8 here? Therefore, it will be divisible. Perfect. Because what I'm trying to say, 968. Well, the other one is 968. Therefore, you are left with B. That B should be divisible by 8. 0 is divisible by 8. Otherwise, 8 is divisible by 8, because B is a single digit. Therefore, you are saying that, look, I have 2 sets of values. I have 2 sets of values. Either it should be closing with 0. The value of B should be 0. Or the value of B should be 8. Alright, that's what you see in all the choices. B is 8 here. B is 0 here. B is 8 here. That's what precisely you see here. Alright, that is what you precisely see there. Okay, alright, fine. Let's add the values, therefore. Let's add the values. Alright, now add this 7, 7, 4, alright, 9, then 5, 8, 9, and 6. That is becoming 55. Alright, that sum is becoming 55. Good. Now divisible rule for 9. If it is becoming 55, you can't make it 54. Alright, next pit stop. Alright, after 55. So you are already at 55. Sum is 55. Then you have an A and you have a B. Basically, what is that you have now? You have 55. You have B and you have A. Now this should be divisible by 9. That's what you are talking about. This entire stuff should be divisible by 9. This should be divisible by 9. Good. If this should be divisible by 9, you already have one case. What is one case? This is 0. Alright, I'm taking this as the case 1, friends. Case 1. Case 1, it is 0. Case 1, already the value is 0. Let us take that. 55 plus 0 plus A should be divisible by 9. Corresponding value of A. Alright, after 55, next pit stop is what? Next pit stop is what? 63. Alright, if it is 63. Right? Yeah. So after this, already no, next pit stop is 63. Therefore 8. Alright, therefore value of A will be 8. Hey, what about the second one? Or what about the second one? Because you are already at 55. You can go up to 63. You may think that, hey, why not up to 72? You can't go to 72 because A is a digit. From 55, you can't jump to 72, which result as 72, because A is a single digit number. From 55 to 72, you got to cross over 10, right? So that is not possible. So therefore A is going to be 8 here. That's one case. Alright, that's one case. By now you got your answer. Alright, by now you got your answer. Just a curiosity, what is the other case? In the other case, you would have written this as 55. Alright, this number, alright, B, you would have taken it as 8. This is case 2, right? You would have taken it as 8, and then you are writing it as 5. Alright, that should be divisible by 9. That should be divisible by 9. Okay, what is 55 plus 8? Alright, 55 plus 8 is 63. If it is 63, the value of A can be 2 more values. A can be either 0 or 9. Technically, 3 sets of solution, my friends. 3 sets of solution, right? 8, 0 is a possibility. That's one pair. The values of A and B can be 8, 0. Second pair, second pair, when the B was at 8, you said the 2 values it can take. It can either take a 0, 8 and 0, or 8 and 0. When B was at 8, it can also take the value as 9. So technically, author knew that there are 3 answers possible. 8, 0 was an answer, 0, 8 was an answer, 9, 8 was an answer. 3 answers. Therefore, you use the word can be. So one of the beautiful question can be, how many pairs of values A and B can take? How many pairs of values A and B can take? That itself is a beautiful question. You may say that 3 pairs. Alright, you will say that man, three pairs of values A and B can take three pairs. Alright, that itself becomes a beautiful question. Alright, therefore knowing the concept is important, because at times the question can be how many pairs of values A and B can take. How many pairs of value. In that case, you should know that it's not that only through answer options I'll be able to solve. Conceptual clarity should be there. Then you can use the answer options depending on the situation. Alright, based on the situation, alright, we can answer it close it faster by using the answer choices. But clarity should be there, because sometimes the nature of the questions that they ask, choices may not be useful. Choices may not be really useful, right? Yeah. Okay, let's go further. Beautiful question. Let's go further. Let's go further here. Let's take a look at this concept. Okay, let's do it together. Let's do it together. Last 15-20 minutes, we'll do it together. Find the maximum value of B such that this particular number is divisible by 11. So what is the divisible by 11? I said that alternate digits. Let me rewrite this. Let me rewrite this number. The number is 2, 6, 8. Then I have a B. Then I have 2, 5 and a C. So what is the divisible rule for 11? I said that okay, start with the units place. Always start with the units place. Let's start with the units place, right? Then we said that go alternate digits, therefore 5 plus C plus 2, or take it as 2C, we'll leave it later. 2 plus 8, 10. This is 12. Therefore you are saying that okay, this is going to be 12 plus C. Sum of the digits starting from the units place is 12 plus C. All right, what is the sum of the digits starting from the tens place? Sum of the alternate digits starting from the tens place. Well, at tens place you have a B here, 5 followed by B. We'll come to that B later. Take 5 in your mind. 5 plus 6, which has become 11. Therefore you are saying that 11 plus B. Fair enough. All right, then you are saying that U minus T, units place minus the minus tens place. You are writing this as 1 plus C minus B. 1 plus C minus B. Now look at the question. Find the maximum value of B. Author is saying that maximum value of B. I said expectation management, my friends. Expectation management. All right, maximum value of B is nothing but the expectation management. Very good. Maximum value of B means can I have a 9 here? That's a thought that comes to your mind. Fair enough. Put 9 and check. If you put 9 here, 1 plus C minus 9 should be divisible by 11. Fair enough. I will take the C value as 8. I'll take the C value as 8. 9 plus 9 becomes 0. 9 plus 9 becomes 0. 0 is divisible by 11. Therefore, I got my answer. The B can take the best value, which is nothing but 9. B can take the best value, which is nothing but 9. Second question, very similar. Only change in the word is this is maximum, which in turn has become minimum. It's the same question. Ditto, same question. But this time he's asking that tell me the minimum value of this, which means till here we'd have arrived till here. Alright, this is the we have arrived till this particular condition. Let's go there. Units place minus tens place is 1 plus C plus B. Right now, this is what I have, 1 plus C plus B. So he's saying that tell me the minimum value of B. Expectation management. Right now, expectation management, we know that okay, this has to be 0. The minima is 0, great. If the minima is 0, 1 plus C should be divisible by 1 plus C minus 0 should be divisible by 11. What is the suitable value of C? Suitable value of C is 10, because 10 plus 1. All right, now you'll say that okay, suitable value of C is 10. 10 plus 1 is 11, but C is a digit, man. C is a digit. C is not a number. C is a digit of a bigger number. If it is a digit, can it take a 10 there? No, it can't. Therefore you said that hey, B cannot take a 0, because if I write 0 there, C is taking a value called 10. It is taking a value called 10. Not possible. Fair enough. So what you do? Increase the counter from 0. You say that let me go to 1. In that case. If 0 is not working, the next pit stop is what? 1, because I'm finding minima. All right, therefore you are saying that 1 plus C minus 1 should be divisible by 11. Oh, it's very encouraging. Now you're happy. All right, reason C can take 0. No problem. 1 plus 0 minus 1, 0 is divisible by 11. Fantastic. Therefore you say that the minimum value is 1. Whether there are options or not for this question, that's our approach. All right, you approach this maximum minima with some expectation. Remember this statement that I made? You generally approach maximum minima with some expectation. A lot of people don't expect anything in maximum minima. See, if it is a plain bland question, don't worry, because anyway there is one answer. But if it is a maximum minima, start with an expectation. So that the closure is faster. More often than not, in most of the questions, if it is a maximum minima, be it quant, or be it logic LR, be it DI, if it is a maximum minima, quickly trigger the thought of expectation. It becomes little faster. So every time you will not be able to expect something. Times you will be able to express, if not 9, at least 8 times. Or at least 8 times. That's what I at least remember from the memory. Fine, let's go further, friends. I hope all of you are clear about this divisibility rules here. All of you are clear about the divisibility rules. Last 15 minutes of the game, last 10-15 minutes of the game on the divisibility. All right, charge up, charge up. Let's finish in the last 15 minutes. Here we go. Okay, any number of the form. This is very important. All right, just a trivia before I continue the divisibility algorithm, just to bring a break. All right, bring back your attention. Any number of the form AB is always divisible by 101. I'll speak more of this. This 101, I will speak more of this 101 in my third lecture. For now, you keep it. Any number of the form AB is divisible by 101. So 101. Just keep it in mind. Any number of this particular form AB should be different? Not necessarily. Or not necessarily. Can I have a number as 2222? Of course, yes. You can have this number as 2222. There is absolutely no problem, which will be divisible by 101. See, think like this. 101 into AB. AB is a digit. Multiply and check what it becomes, my friend. All right, what it becomes. AB is a 2-digit number. Check it. All right, it becomes AB and AB. Okay, take a number for that matter. 101 into 23. Check it. What does it become? 23 and 23. Right. So therefore, it is of the form AB. Pretty simple one. Pretty simple one. But sometimes it skips the mind. Sometimes it skips the mind. All right, therefore, it's important there. Okay, this is the beautiful number. I love this. All right, because this is examiner's favorite. 1001 is one of the examiner's favorite numbers. Okay, here I will just tell a quick story about this 1001. In the sense, I'll spend a little more time on 1001. I want you, all of you, to remember this particular number. All of you to remember this particular number. Look at that. If it is 1001, see, basically what I'm trying to say is 10 power 2. 10 power 2 plus 1. Any number of the form 10 power 2 plus 1. If it is 10 power 2, alright, if it is 10 power 2, write 2 digits AB, AB. You wrote it as AB and AB. Therefore, it will be divisible by 101. So now what is this 1001? This is 10 power 3 plus 1. If it is 10 power 3 plus 1, break it like this. It will be of the form ABC, ABC. If you write any number of the form ABC, ABC, it will be divisible by 1001. Hey, should A, B, C be necessarily distinct? Not necessarily distinct. Can I write the number as 333? And 333 works. Hey, can I write this number as 323 and 323? Yes, it works. Yes, it works. I didn't say that ABC should be the distinct digits, but you drop that line. All right, line. How do you understand that at 3 I should drop the line? Because it's 10 power 3. All right, it's 10 power 3. Okay. Now this is the tip of the iceberg. I will talk in detail about this at a later stage. At a later stage, I will talk in much more in detail. That's in the third lecture. Right, today we're in the first lecture. All right, let's understand this point. 1001. Let me come back to this. This 1001 is a product of 3 consecutive prime numbers. All right, 3 consecutive prime numbers. 1001, beautiful number. It's a product of 3 consecutive prime numbers, that is 7, 11 and 13. 7, 11 and 13. 1001 is a product of 3 consecutive prime numbers, that is 7, 11 and 13. Just remember this, by heart this for now, right? By heart this during this particular lecture. When I come to the deeper lecture, I will tell you the implication of this. Applications and implications, I will talk of that. Okay, 7, 11 and 13, which implies, all right, those who know a little bit about the factors, it has 8 factors. All right, it has 8 factors. 1001 would have 8 factors. If 1001 can be written as 7, 11 and 13, there are the factors. Factors, what are the factors here? 1 is a factor of 1001. 1 divides 1001, right? So 1 divides it, 7 divides it, 11 divides it, 13 divides it, 77 divides it, 91 divides it, 143 divides it, and 1001 also divides it. Okay, 1001 also divides it. I want you to remember this list also. This list of 8 numbers are also very important for us in aptitude. List of these 8 numbers are very important, right? Yeah. So 1001 is important. All right, because we also need to understand that it's a product of 3 consecutive prime numbers. All right, second thing that is important here is also it has 8 factors, and you should know the factors. When you look at 7, 1001 should come into your mind. You look at 11, still 1001 should come into your mind. You look at 13, 1001 should come into your mind. Okay, it comes to my mind, and do what? That I will tell later. But let it come to your mind first. Let it come to your mind, then do what with that after coming to my mind, what I should do. We'll see when the application comes. All right, when there is an application, we'll see. Okay, simple example. Close it, friends. Close it. Close it. If you have held my point, close it. Close it. 10 seconds. Close it. Got the answer? Which of the following is a factor of this number? Got the answer? Which of the following is the factor? Good, very good. Yeah, now this number can be written as 841. This number can be written as 841 into 1001. 841 into 1001. That's how it can be written. Now I already told you about this 1001 factor means what? Already 841 factors also possible, 1001 factors also possible, but readily you will know that okay, 1001, 143 is a factor. 143 is a factor of this number. Let's close it. All right, once I know that 141 is a one, this is a factor of that number, we'll close it. All right, we'll close it there. Okay, let's proceed. All right, it's just a break, pit stop here. Now understand the division algorithm, friends. I'm going to stop with this. All right, I'm going to stop with this. Maybe I'll spend 5-10 minutes on this. 10 minutes, right? In 10 minutes from now, we are going to close this lecture. In 10 minutes, we will close. Right? Division algorithm is important. What is that? I will brief you. I will take few examples on the division algorithm, and we are done for the day. Okay, let's take here number. If I have a number, there is a number divisor. You will have a quotient. You would have a remainder. So how do you express this thought? Number is equal to, therefore number is equal to divisor into quotient plus remainder. Right? That's how you apply the division algorithm. When do you learn? Class 5 or class 6. Based on the board, by the time you go to class 5 or class 6, you'll be pretty much clear. Class 5 only, all right, not even class 6. All right, class 6 would be too late. All right, it is class 4 or class 5. You learn that during the class 4 or class 5, number can be written as divisor into quotient plus remainder. Right, so that's a division algorithm. I guess everybody is clear about this. All right, you can take your own small numbers. All right, just in case, all right, it's long time you did some math, put that to perspective, but remember this now. All right, right now you remember this. Number is written as the divisor into quotient plus remainder. Let's see the applications built on this. Let's take some small numbers built on this. Look, all right, author is saying that, hey, there is a number when divided by 28. All right, now there are, because some small questions are built on this, I will progress. Right, as I go to the third and fourth example, I will progress to what is the kind of application I want you to remember there. A number when divided by 28. A number when divided by 28 leaves 20 as the remainder. His question is, when the same number is divided by 7, what is the remainder that is going to be? How do I write my number, friends? How do I write my number? My number is 28 times of a quotient. There is a 28 here, 28 times of a quotient plus 20. All right, plus 20. Very good. All right, divided by 7. Divided by 7 means what? Number should be divided by 7. If you are dividing this by 7, this should be divided by 7. This should be divided by 7. Divide throughout by 7. Divide throughout by 7. Therefore, when the number is divided by 7, look what is the remainder from here. 28 is anyway divisible by 7. This 28 is completely divisible by 7. 0, irrespective of what is the value of q. Irrespective of this q, that is 0. Very good. Plus, when 20 is divided by 7, the remainder is 6. Remainder is 6. Can the remainders be added like that? Of course, yes. Of course, yes. That's what you are doing. Therefore, when the number is divided by 7, you are saying that 0 plus 6. Therefore, the remainder is 6. Therefore, the remainder is 6. Simple way of expressing the division algorithm. All right, therefore, 0 plus 6. Very good. Now, look at this, the next one. Let's take a look at the next one. A number, when divided by 28, the remainder is 20. How do you write? 28 plus q plus 20. First statement is same as the previous statement. This time, what did he say? He is saying that n, when it is divided by 5, very good, he is saying that divide this by 5. I'll divide this by 5 and I will divide this by 5. Hey, what did you get here? This remainder is 0. When 20 is divided by 4, what is the remainder, friends? It is 0. Okay. When 28q is divided by 5, what is the remainder, friends? Now listen, when 28 is divided by 5, 3 is the remainder. Take this 28, divide this by 5. What's the remainder? 3 is the remainder. Very good. But what about this q? Don't know. Therefore, that q comes as it is. Therefore, now you are trying to say that when n is divided by 5, the remainder will be of the form 3q. If it is 3q, you can't answer. Why you can't answer? Now put q is equal to 1. Your remainder is of the form 3q when divided by 5, right? When divided by 5. Good. So now put q is equal to 1. Put q is equal to 1. Remainder is 3. Okay. Put q is equal to 2. Put q is equal to 2, remainder is 3 into 2, 6. 6 means what? Divide by 5, because you can't say that, hey, when you are dividing by 5, how you are getting 6 as the remainder, correct? I know, you know. All right, therefore it cannot be, therefore divide by 5, make it smaller than that, becomes 1. So now look, already you are already having two claims. Once you said remainder is 3, another time you are saying remainder is 1. Therefore what? Remainder can't be determined. All right, there is no unique answer to this. All right, there is no unique answer to this. Why? Put q is equal to 3, you will get another answer. You will get already, you will get the answer as 4. Therefore, you say that, man, all right, I'm getting multiple answers here. Multiple answers here. It cannot be determined. Now, remember this point. All right, point number 1. Point number 1. When it is divided by 28, okay, Point number one, I want you to remember this point. I make 2-3 points here. Before we close this lecture, I'll make 2-3 points. All right, point number one, if 28, if you take the factor of that number, then the remainder can be found out. All right, if they divided by n, what if you divide by the factor of the divisor? All right, when n is divided by 28, if you divide by its factor, remainder can be found. Now there is a 28. Is 5 the factor? No, 5 is not the factor of 28. Therefore, a unique remainder cannot be found. More often than not, a unique remainder cannot be found. That's a point I want you to remember. All right, that's a point number one. Point number one is, all right, when the number is divided by a divisor, if you divide it by its factor, then the remainder can be found. But if you divide it, all right, by not its factor, which means like here 5, which was not a factor of 28, then it cannot be found out. All right, then it cannot be found out. Point number one. All right, let's go to the second point here, friends. Let's go to the second point. N divided by 5, the remainder is 3. 3 times of n divided by 5. Mathematically, how do you write it? How do you write it? There is a number. When divided by 5 means 5 times of cube plus 3. Fantastic. All right, then what you are trying to say? Same n, 3 times of n author said. Therefore, multiply throughout by 3. Multiply this entire equation by 3 because author said 3n this time. All right, 3n, which means this becomes 5 into 3. All right, sorry, all right, 3 and 5 into 3 times. All right, 5q into 3 basically 5q into 3. What this becomes 3 into 3. Why? Because you have to multiply both sides by 3. You can't say that, hey, only on left hand side I will multiply by 3, right side I will not do. Better you do both the sides. Alright, you got to do both the sides. Okay, what did author say after this? Divide by the same number. Divide by the same number. 5 here, therefore 5 here, therefore 5 here. Therefore 5 here. Therefore listen to this. Alright, now this is 0. This leaves me the remainder 0. This leaves the remainder 0. Why? There is a 5 here and there is a 5 here. Alright, therefore the new, that is a multiple of 5. Yeah, that's a multiple of 5. What is this here? 9 by 5. What is 9 by 5 remainder? 4. What is a 9 by 5 remainder? Alright, that's going to be 4. This plus sign, add it as it is. Therefore, what is 0 plus 4? It is 4. Now listen to this, friends. I want you to remember like this. Hereafter, it's not a numerator and denominator. I just want you to remember it like this. I want you to remember it like this. When the number is divided by divisor, leaves r as the remainder. Let's say given. This is given to us. Given when the number is divided by the divisor, leaves r as the remainder, then the same number, already if k times of the number is divided by the divisor, remainder becomes k times of r. Remainder becomes k times of r. Fundamentally, I want you to remember this statement. Now let us see what is the implication of this. Alright, what is the implication of this? Let's go to this number here. There is a number when divided by 5, 3 was the remainder. That's my first statement. When the number is divided by 5, 3 is the remainder. Good. 3 times of the number. Fine. 3 times of the number when divided by the same divisor. Hey, I'm expressing the same thought. I'm not doing anything. I'm expressing the same thought in an alternate fashion. Right? Same number when divided by 5. 3 times of the number when divided by 5. Fine. The remainder should become 3 times. 3 times. Now you will say that 9 is the answer. Good. All right, 9 cannot be the answer. Why? Because your divisor is 5. How your answer can be 9? Therefore, what did you do? You got 9 here. Therefore, you say that, hey, let me divide by 5. Therefore, 9 by 5. My result will become how much? 4. That's how you do. Right? That's how you do. You don't have to write this algorithm hereafter. Don't write this algorithm hereafter. All right, now just write this point. Let me go back to the previous question. Let me illustrate very similar to this. Let me illustrate similar to this. When there is a number, all right, what you are trying to say here? A number when divided by 28, it has left 20 as the remainder. It has left 20 as the remainder. Question. With the same number divided by the factor of 28. Factor of this 28. Alright, just you got to do is 20 divided by factor of 28. What is the remainder? Factor of that number. Factor of the divisor. When the number is divided by divisor, let me write the generic form, my friends. Let me write the generic form. When the number is divided by the divisor, leaves r as the remainder. This is given. Let's say given when the number is divided by divisor, leaves r as the remainder. Then when the number is divided by its factor of the divisor, not the divisor, its factor, then all you got to do is your answer is going to be r divided by factor of the divisor, list the final remainder. List the final remainder. That's all you would have done here. Now let me illustrate this. Let me write this number. What is given to me? Number divided by 28. 20 is the remainder. That's the first statement. Now what did you say? 7. I just have to check that is 7 the factor of 28. Answer yes, it is the factor. Therefore just take this 20 here, remainder 20 divided by 7. 20 divided by 7. 6 is the answer. That's all I wanted you to do. These properties I want you to remember because we are going to apply it in a mega scale. Mega scale. What we are doing here is a small prototype testing. Alright, small prototype. Point number 1 is this. Alright, this one property. Alright, this another property, right? Another property. This one, boxed one. This is another property. right? There is a two properties here, right? These are the two properties I want you to remember there. Okay, next one, 3. All right, n divided by 5, the remainder is 3. N square divided by 5, what is the remainder? I already told you how to write the division algorithm. Hereafter, please remember this property again. Given that, alright, given that when the number is divided by the divisor, leaves r as the remainder. When n raised to power k is divided by the divisor, your remainder becomes r raised to power k. Binomial expansion, friends, just a binomial expansion, no big deal about it. Alright, n raised to power k when divided by d, alright, it becomes r raised to power k. Given this, you can derive this. Alright, given this expression, alright, you can get this part. Alright, now just like you did earlier, what did you learn earlier? When the n is divided by d, leaves the remainder r. Last slide you also said that, okay, therefore when k times of the n is divided by d, the remainder is going to be k times of r. That's what you learned in the previous slide. So now what you are trying to say, if it is n is raised to the power k, r will be raised to the power k. Alright, let's take a look at this example now. Let's take a look at this example. When there is a number divided by a divisor, leaves 5 as the remainder. It's an expression of a thought. It's the same division algorithm. I'm expressing it little differently in a concise manner, right? Yeah, n by d leaves 3 as the remainder. When n divided by 5 leaves 3 as the remainder. Good. N square, all right, n square divided by 5. N square divided by 5. The remainder has to be 3 square. The remainder has to be 3 square because you did a square here. Just do the square here also, 3 square. Hey, what if it is a cube? Then you do cube, right? 3 square. Okay, but the point here is you should always give an answer less than the divisor, right? So now you will say that, hey, what is 3 square, man? 9. Hey, you can't give me an answer 9 when you are dividing by 5. Sure. So make it lesser. Divide this by 5 until the final remainder, which is going to be 4. Right now, this is another property after this. Done. We are fairly done. All right, we are fairly done with this. Okay, now listen to this. When there is a number, all right, if there is a number 1 number, all right, now divided by a divisor, first number, all right, there is a second number, all right, assume that there are multiple numbers, all right, first number when multiple numbers. Okay, let me take it one at a time. When the first number is divided by a divisor, leaves r1 as the remainder. Let's say when the given this, all right, now this is given. Second number when divided this, all right, these pieces are given. Second number when divided by the divisor, leaves r2 as the remainder. When I add both the numbers, if I do n1 plus n2 undivided by the divisor, if I divide by the divisor, given these two were given, let's say, hey, can there be n3 also? Of course there can be n3 also. I'm just writing two of them to illustrate. N1 plus n2, what if I add both the numbers and divide by d? Your result is going to be r1 plus r2. Your result is going to be r1 plus r2 because you added these two bits, therefore you are going to add these two bits as well. What if you subtracted? Subtract. What if you have multiplied? Multiply, which means what? Plus is fine, minus is fine, into is also fine. Now you may say that a division is also fine. No, don't divide, because what you are doing is division, friends. Now don't put another division into the division. Addition is fine, multiplication is fine, subtraction is fine. All right, I want you to remember this particular rule. Fine, let's come here with this understanding. Let's come into this. All right, there is a number when divided by a certain divisor, leaves the remainder as 23. Certain divisor leaves the remainder as 23. All right, yeah. So when twice the number, this is already done, this is already covered. All right, this is already covered here. All right, this is already covered here. Okay, this is a different kind of example. Just remember this property. Now don't relate with this example. This example is not to do with this. I wanted you to relate. All right, remember this. Let's see the next slide. If I have an example, we will see this. Okay, I'm extending the class by another 5 minutes. Let's close this so that in the next lecture I will start with LCM. I can start with LCM. Let me close this. All right, now because of that 5 minutes, let's not truncate it soon. All right, let me close this. A number when divided by a certain divisor. Let's go to this question, friends. A number when divided by a certain divisor, leaves 23 as the remainder. Fair enough. When twice the number is divided by the same divisor, what is that author is trying to say? Twice the number is divided by the same divisor, leave what author is saying. What you know that the remainder also should get doubled because the number got doubled. If the number got doubled, according to you, the remainder should get doubled. Fantastic. Therefore, already now 23 into 2, you are expecting a 46. But what did author say? Hey, it has become 11. It has become 11. By now you know why it has become 11, because this is more than the divisor. If it is more than the divisor, you generally divide it by the divisor and you will tell the answer. Generally you will divide it by the divisor and you will tell the answer. Good. So now think about this, guys. There is a 46. You divided by a divisor and you are saying that 11 is the remainder. What is the possible value of the divisor? 35. How do you get this? 46 minus 11. Take this 46, subtract it, you will get the one of the values of the divisor, which is nothing but 35. One of the values is therefore nothing but 35. So what you are trying to say, 46 when divided by 35, the remainder is 11. Alright, remainder is 11. You may say that, hey, is it only 35? Yes, alright, now 35, because the factors of 35 are factors. Okay, let me not confuse you at this stage. Take it as 35. We will talk about it at a later stage. Therefore, what is the divisor here? 35. So one check that you do is what? Alright, you look at this 35. Alright, look at this 35. So is this remainder that you got as 23, was it also less than that? Yes, because every remainder should be less than the divisor, right? So therefore, this was the remainder which is less than 35. This is also a remainder which is less than 35. You need to be mindful before giving the answer. You need to be a little mindful. We cannot outrightly shout some answer as the answer there, right? Some number as the answer there. Let's take a look here, friends. Let's take a look here. In fact, the property I told here, I was talking about this. This was the one. I'll let this property apply it in this slide. Let's apply it here. Let's apply it over here. Let's apply it. A number when divided by a certain divisor leaves a remainder of 10. Another number, all right, there is a number and there is another number. There are two numbers technically here, right? Two numbers, a number and there is another number. Another number when divided by the same divisor is same, leaves 12 as the remainder, which means what? There is a n1. When divided by a divisor, it has left the remainder of 10. There is another number n2. When divided by the same divisor, it left 12 as the remainder. When sum of the numbers is divided by the same divisor, the remainder has become 9. So what do you mean? All right, add them. I already told the algorithm. n1 plus n2 divided by d. The remainder is going to be addition of these remainders, 10 and 12. All right, 10 plus 12. 10 plus 12. That's what I was expecting. I was expecting a 22. I was expecting a 22, but what did the author say? Author said that, man, it is not 22, it is 9. Alright, he's saying that it is not 22, it is 9. Fair enough. So which means the divisor was lesser. Sure enough. So what happened here? You divided it by a divisor. Therefore, it has become 9 there. 22, you divided this by one of the divisors. Therefore, the result has become 9 there. 22 by divisor has become 9. So what does it mean here? Same way, 22 minus 9 is one of the divisors. One of the divisors has to be 22 minus 9. Difference between them, which is nothing but 13. Alright, therefore, you are saying that it is 13. 13 is one of the divisors. 22 when divided by 13, 9 becomes the divisor, 9 becomes the remainder. Always before giving an answer, always have a check here. 13 is the divisor. Look at the remainders. Every remainder should be less than whatever you are answering. So every single remainder has to be less than the divisor. Fair enough. All remainders are less than the divisor. Alright, all of them are less than the remainder, less than the divisor. There we are with our answers. Okay, yeah, I hope all of you had a great learning here. Alright, all of you had a great learning here. I covered classification in this particular lecture, and then I went on to cover the divisibility in this lecture. I'll start with the LCM in my next lecture. Start doing the homeworks. Alright, now start doing a little bit of work. Start hitting a little bit of depth based on these particular concept. What is that? On divisibility and on classification. So start solving few questions in your modules based on this. Alright, after the next lecture, you will have massive, enough things to do in your classwork and in your homework. Right, here we go. So all of you have a blessed day. All right, I will take leave from you. Tata, bye bye. I will see you in my next lecture. All right, bye till then. Stay blessed.